in the afternoon, we are going to introduce you to the 3D visions, 3D deep learning. All right, so we are going to touch a little bit about that. So maybe in case you're interested in the futures. Okay, so in this morning, in the morning, so we are going to learn about some sort of basic introductions to generative models, that is autoencoders, variational autoencoders, and generative adversarial networks, or GAN, as we know. So these are the very basic, and these are the foundations of most of the generative models that we are using today, right? So so if we're going back to the categories of supervised and unsupervised learning, right? So when we talk about the supervised learning, right? So when we talk about supervised learning, we are saying that we have a data set as X is the data and Y is the labels. So the goal of the supervised learning is that we want to find some functions, that is a mapping functions from X to Y, right? So if we give an X input or X data into some function F, so what we are expecting from that is the output of Y that is correctly predict as the labels of the data, right? So this sort of example of this kind of task would be a classification task. For example, image classifications, object detection. So we feed in the input image, that is X, pass it into some sort of models, that is some sort of functions, right? Some sort of functions, so that it gives us the labels Y that is corresponding to the ground truth of our data, or even though such as semantic segmentations. So this can be seen as the supervised learning, right? Because we have both X and Y, so that the model learn mapping functions from X and Y. So then it can generalize to others, to other data that is never seen before. Okay. So for the unsupervised learning, so the unsupervised learning, the difference here is that we have just data, no labels, right? We have only X, and then there's no label Y given to the models. So the goal is that we want to learn some underlying hidden structure of the data. So that's what we want to learn. Instead of learning a function mapping from X to Y, so what we want to learn if you're doing unsupervised learning is the structure, some hidden patterns or hidden structure of the data. All right. So the example of unsupervised learning would be clusterings, dimensionality reduction, features learning, density estimations. So these are the difference between unsupervised learning. So unsupervised learning means that you have only data but no labels. Okay. So here's the example of unsupervised learning, right? So yesterday we discussed about k-means clustering. So these are the example of unsupervised learning. We have only data but no labels, right? So we don't know which data point will belong to which cluster. So we just want the models to learn how to group this data point together into a similar group. So k-mean clustering is some sort of unsupervised learning, right? Or dimensionality reductions, like the PCA, principal component analysis. Also another example of unsupervised learning, where we are mapping some features from 3D to 2D, so that the different features fall into different categories. So these are another example of unsupervised learning. Okay. And another example of unsupervised learning would be features learning. So the example of this model would be autoencoders, right? So autoencoders, what we have is just the input, right? What we have is just the input, and then the goal of autoencoder is to learn some low dimensional features of the image. And then after that, we are being able to reconstruct the input image, so that the input and the output is very similar, right? So autoencoder is nothing but learning the features of the input so that we can sample that to regenerate the input again. So that's the autoencoder. So autoencoder is an unsupervised learning models. All right, so we just have we have only data but no labels. So autoencoders doesn't predict anything. It just reconstruct the original data. All right, so what another way that we can say about autoencoder is that it compressed the input data into a lower dimensions, right? For example, if you have the image of 400 by 400, right? So that will be 1600,000 dimensions. So when you design the autoencoder, you could probably make the model compress the data up like down to like 20 dimensions, from 100,000 to 20 dimensions, and then you want the model to take that 20 dimensions and then reconstruct it back to 160,000 dimensions. So that's the autoencoders, right? So but another way that we can look at the models in general, right? Instead of the way that they are learning, either supervised or unsupervised learning. Another way that we can look at, or we can categorize the models, would be how they are interacting with the data, right? So we can categorize them in terms of discriminative and generative models, right? So the discriminative models would be the models that learn the probability distributions, right? The models that learn a probability distributions P of Y given X. That this means that if we give the data X into the models, so the models will predict the probability of that data being in one class. All right, so if you're talking about this sort of models, it would be image classifications, object detections. So these are the discriminative models, because we are giving the models some sort of input, and then the model just predict the probability of whether the image belong to which class, or the image belong to which objects that we want to detect. On the other hand, the generative model is just learning a probability distributions of P of X, right? So it just learn how the underlying distributions of the input is. All right, so that's the generative models, which means that if we have a set of data, the model is going to learn how to represent this data in some sort of probability distribution. So later on, we can take any sample from these distributions and then regenerate the data. So the autoencoder as an example. So we have the input data X, and then we want the models to learn the distributions of this. And then later on, we want the models to be able to take some sample from these distributions, and then regenerate the input data from these low dimensional variables. And another way that we can look at it is the conditional generative models, that is learning a probability of learning a probability distributions P of X given Y. So if we want the models to generate something, so we are giving it some hint, some sort of hint, so that the models knows what is data about. For example, if we want the models to sample some data from some distributions, right? And then we also give the additional information to the model that the sample that you are taking from this distribution should be some sort of cat or something. So the models knows how to generate a cat. All right. So because we give it a hint. So this is how you can look at the models in another way. So what we have been discussing is that the models, we can categorize the deep learning models into two ways. First, the way they learn, right? Supervised or unsupervised learning, and how they're doing the task. They are doing discriminative tasks or they are doing generative tasks, right? So the discriminative, it just like we want to classify the dog and cat, for example. So what we are giving in is the image, and then the model will give us the probability of the image being dog or cat, right? So that's the discriminative models. And for the generative models, so we are giving in the so here's another example. If you are giving in the image of the dog, so the probability of the image being a dog should be higher the probability of the cat. Good morning. And so also here's another example. So for example here, you can see that if our models is able to classify or discriminate between dog and cat, given the image that is out of the range, that is giving a monkey. So the discriminative models has no way to handle this out of range models, right? So it gives all the label to every image that is being able to classify. So if we give some sort of unreasonable input, it won't be able to handle that. So yeah. And the for the generative models, it's just like all possible image can be compete with each others, so that the model needs a deep understanding of the image, whether it is a dog and a dog sit or stand, how many legs are there, something like that. All right. So so the models for the generative model can reject the unreasonable input by assigning to a very small value. Right? For example, if our models is only learn to generate the image of a cat and a dog, so the image of a monkey and some sort of art image here, they will have a really very low value for the probability because it's out of range from the models. Okay. So for the conditional generative models, it is nothing but very much the same as the generative models. But what we are giving is we are given the label. We are given the labels to the model as well, so that it knows what we want it actually to generate. Right? We just give it a conditions. A better conditions, we give it additional conditions to the models so that it can generate the output for us. So all of these models seem to be very distinct. All of these models seem very distinct. So if we look at the probability distributions equations here, for the discriminative models, it is P of y given x. And then for the generative model is P of x. And for the conditional generative model, it's just P of x given y. So it look very similar. So, right? So they seem very distinct. I mean, they seem very different, but actually they are not fully distinct. Okay. So if you look at the Bayes rule did some sort of distributions. This is the Bayes rule, right? So we can see that the probability of x given y is equal to the probability of y given x divided by probability of y multiplied with probability of x. All right. So what we can see from here is that we can say that we can build a conditional generative models from other components, right? So probability of y given x, this is nothing but a discriminative models. All right. And probability of x is nothing but a generative models. All right. and the probability of Y is just prior over the labels. So if we group this together, if we know the answer for all of these models, we can build the conditional generative model from this. So to size, for the discriminative models, it assigns a label to a data. All right, so this is what we call a features learning. It learns to extract a features from the data and then assign the label to each individual data point. All right. And for the generative models, it basically mainly used for detect and outliers or features learning, but without labels. All right. And it is also being used to sample to generate a new data. Right. So that's why it's called generative models. And for the conditional generative models, it is assign a label while rejecting the outliers. So it generates a new data with conditions on some sort of input labels. Right. So these are the different type of these are the difference between discriminative and generative models. So if we look at the taxonomies of generative models, there are many ways that we can look at either as the explicit or implicit density. Right. So there are many varieties of generative models. But what we are focusing today, we are going to focus on the variational autoencoders and generative adversarial network. So let's start with the variational autoencoders first. So if you look at the word variational autoencoders, there's the word autoencoders, right? So before we go to variational autoencoder, let's talk about the autoencoder, just a regular non-variational. So the autoencoder, it is the unsupervised method for learning feature vectors for raw data, right? Without any labels, right? So autoencoding itself means encoding itself. So how do we mean by that? First, we have a set of data, right? We have a set of data consists of many image, that is X. So we pass this into what we call an encoders. Right? We pass this into what we call encoders. So encoder could be anything. For example, CNN fully connected layers, and a series of CNN layers or fully connected layers. So the encoders will try to extract some features or try to extract some useful information from the input, right? So. And then what we get from the encoders is the features, right? So the model is trying to extract only the useful information from the input, all right? So that's what the encoder does. So the problem here is that how can we learn this features transform from raw data, right? Because we have this set of data X, and then we pass this into that one. So the problem is, since we doesn't have any label for each image, right? So the question is, how can we learn this features transform from the raw data? So the idea here is that instead of having the labels, right? So we want the models to reconstruct the input data with decoders, right? So we have the encoders to encode or learn the features, only the useful features, as this is what we call a latent vectors, okay? Sometimes you bring here a latent vectors or features, Z. And then we have another component that is called decoders, right? So the decoder take in features vectors or latent vectors Z, and then it will try to reconstruct the input data, right? It try to reconstruct the input data X hat over here. All right, so what we get out is the reconstructed versions of the input. All right, so keep in mind that we have only input data without any labels. So to learn features transform, instead of having a labels, right? Instead of having a labels, the model just learn how to reconstruct the image, so that during this learning, it knows what are the useful feature it should keep. All right. In this latent vectors here, the model learns to keep only the useful information, so that it can reconstruct the output to be as similar as to the input. Right. So to summarize, the encoder learn a mapping from a data X to a low dimensional latent space Z, and then the decoder learn a mapping back from latent space Z to reconstruct the input or reconstruct the observations X hat. So that's the autoencoders. Okay. So so the question is, how can we measure the performance of the model, right? So to measure the performance of the models here, we just simply use the output distance to compare the similarity between input and output pixel by pixel, right? So that's it. So how to measure the performance of the models, we just use the output as a loss function. So what we need the model to do is, the model have to try to reconstruct the most similar output to be as similar as the input. All right. So here is the example of autoencoders using the different size of latent vectors. All right. So the latent space here affect the performance of the reconstructed, or affect the quality of the data that we're trying to reconstruct. So for example, here's the 2D latent space. 2D means that, for example, let me give you a concrete example here. So for example, our input image, we have 400 by 400 resolutions. Okay. So if you look at it in terms of the vectors dimensions, it would be equal to how much? 1600,000, right? 1600,000 dimension vectors, right? 16. So the models here is trying to compress to a lower dimension, right? So for example, here, if we are saying that we want the model to learn, try to compress or try to extract the data from this 160,000 dimension down to 2 dimensions vectors, only 2-dimensional vectors, right? Which means that only, for example, x1, z1 and z2. That's it. And then from these 2-dimensional vectors, we want the decoders to reconstruct it back to 1600,000 dimensional vectors, right? So what do we mean by that? So that's why we are saying that the size of the latent vector affect the reconstructed data, which means that the smaller the latent vector, the poor quality of the reconstructed data we have, right? So if we increase from 2D to 5D latent space, we can see that we can achieve a better quality of the reconstructed data. So it affects the quality of the latent space, affect the quality of the reconstructed data. All right. So here's the latent space of MNIST data set we just saw. So imagine latent means hidden, right? Latent means hidden. So you might be confused why I'm talking about like low dimensional data space, what is feature space, what is latent space, right? So when we talk about space, this is one space of the image, right? So this space would be X and Y space. So, or it can be a Euclidean space. And then whenever we are passing this image into a CNN layer, which means that we are doing some sort of transformations. It converting the image, right? It converting the image from Euclidean space into another space. Another space, for example, if you have 1600,000 dimensional space, and then you perform a CNN with 64 filters, which means that you are transforming 16,000 dimensions to 64 dimensions feature space, right? So this feature space, or we call latent space, it's some sort of hidden space that we cannot see, is unknown to us, right? It's just another space, right? Just another space. So we are trying to project this data space into some sort of hidden space over here. So after model learn, we can visualize how is this latent space looks like. All right. So this is the latent space of the MNIST data set. As you can see, the model is trying to group the data, trying to group the image of the same numbers, right, of the same number together. For example, here is the group of which is number one image. Here's the group of number two image. Number 0. And these are the group of number 7. Right. So if we have the image, of the handwritten digit, and then we pass this into the encoder, and then it finally end up into this space. So this is what we call the latent, right? And then after that, we have a decoder that is trying to sample or pick up any point in this space. So we expect that if it is picking up any point from this group and then pass this point into the decoders, what we are expecting back here is the number 1 digit, right? So if it is pick any point from this group and then pass that into a decoders, we are expecting that the resulted or the reconstructed digit would be 0. Right. So that's how the autoencoder works. Right. So after training, after training these autoencoders, we can just throw away these decoders, and then we can use these encoders for some other tasks, right? Because what the encoder learn how to extract a very useful, only useful information, it's keep only useful information from the input. That's what it learned. So it just throw away some sorts of noise from our input. So it keep only that. So which means that we can use the encoders for some other tasks. Right. So for example, what can we use the encoder for? Okay. So we can use the encoders, so we can stack the encoder with a classifiers. Okay. Because the encoder it is good at extracting a very useful features from the input image, so that we can use these encoders and then stacking the classifiers, right? A classifier would be, for example, just a set of fully connected layers, so that we can use this as a classifications network, classification models, right? We can reuse this part of the encoder because it's only learn how to compress the data. It's only learn how to extract only useful information. So then we can just stack this classifier and then use the entire models here as classification models. Okay.
Sorry. So the encoder is it like convolution filters to downsampling? I mean, resize a bit into small latent space, and then after that you apply the classifier FCN fully connected.
Yeah,
Even
right.
matter like I mean softmax or whatever to get a classification, right?
So why do we have to do this? Why can't we just train the model with supervised learning, right? So for example, let's say that we have a set of data. We have a set of data, right? Let's say we have millions of images, and then we have only like 10,000 of them have a label, right? So we have 1 million. And then we have only 10,000 of those millions have a label, whether this image belong to dog, this image belong to a bird, this image belong to a deer, or something like that. We have only those 10,000 labels out of 1 million. So what we have to do first, we can use autoencoders trying to learn the features, trying to learn how to extract features from these 999,000 images. All right, you use that to learn from there, and then later on you use the 10,000 image with the labels to retrain the models, to fine tune the model, the entire models, so that you can utilize the encoders as the features extractors, and then use that for the classifier models, because you have only small portions of the image being labeled, right? So this is what we call semi-supervised learning.
Okay.
So you get the idea. So this model, this encoder is learning from let's say that 990,000 images, right? It's learning to extract features from these many images. So now we get this sort of models with some sort of weight initialized supervised model, right? And then this part we just stacking fully connected layers, and then we retrain these entire models. We retrain these entire models with another 10,000 images, which has a label Y. We retrain this entire, right? So that the models being able to classify the image later on, right? Because most of them are without label. So if we are doing the supervised learning, we won't be able to achieve that because we already have 10,000 images with label. Okay.
Clear. Thank you.
So another applications autoencoder would be the dimensionality detections and features extractions, right? So what do we mean by the dimensionality detection is that let's say that we have the image of 400 by 400, so that's 16,000. That is 16,000 dimensions, right? And then we use autoencoder to compress the image down to probably 100 dimensions. So that's what we call dimensionality reductions. Okay, so we can use autoencoder to do that. And also we can use the autoencoder to extract some features like I mentioned before, for that, so that we later can be classified as these as classification models. And another applications of autoencoder would be denoising, right? Image denoising. So for example, we have this the image without noise, and then we added some noise, right? We probably add a salt and pepper noise, and then we feed it the noisy image into the models, right? So the models, the autoencoder will regenerate the image again, so that we measure the reconstructed image with the image without noise, right? With the image. So it is going to reconstruct this another image, right? And then we compare this to the one that without noise. So when we keep training this one, the model is going to know that we want the model to remove any salt and pepper noise that we are added into this, because we don't compare it into with the noise one. We compare it with the a better version, so that the models can learn how to denoise the image, right? So you get the idea, right? So we add the noise, and then we pass this noisy image into models, into autoencoders, and then it regenerate another image. We compare this reconstructed image with the original image over here, and then we keep doing this for every sample in our data set, right? So the model will learn how to compress, or will learn how to denoise this noise from our image. So that's why we call denoising application. So similarly, it can be used to detect anomaly, which means something that out of range. Yeah. So but there's a problem, right? There's a problem with autoencoders here. So the autoencoder, it's learned the latent features for the data without any label. That's what it does. And it can also use features to initialize the supervised models, like classification models, right? And as you might see in that the autoencoders, right? Autoencoders, it has no way to be able to sample a new data. To sample, what do we mean by a new data? So if you remember the latent space of the MNIST dataset, right? So we have some sort of a group of a group of vectors, right? A group of vectors, which means that we are mapping this 1600,000 dimensional vectors to, for example, 5-dimensional vectors. All right, so this is what the encoder does. And then to feed these latent vectors, from this latent space into a decoder, we just sample a vectors. All right, we just sample a vectors. We're just grabbing the vector that we already mapped, right, from this space, and then feed it into the decoder to reconstruct the new data. All right. So what do we mean by no way to sample new data? Because if you look at this space, right? If you look at this space, what the model is going to sample is each and individual dot that is already project onto these latent vectors. But what it cannot do is that it cannot sample this point, this empty point. This is what we call a new data. It cannot do that, right? Because it has no way to know what is this one, because what it does is just projecting every image into this area, but not this area. Right. So that is the problems of autoencoders, right? So yeah, like I mentioned here, if we are going to, there's a gap, right? There's a gap in the latent space where the data never been mapped to. So if we want to sample the latent vectors in the latent space that never be seen by the decoder before during the training, so the output might not be makes any sense, right? So we cannot generate a new sample from there. Okay. So that's bring us to variational autoencoders. Okay. So variational autoencoders, what we are going to do here, we are going to introduce probabilistic to autoencoders. All right, which means that instead of predicting, or instead of encoding a feature space or latent vectors, the encoders is trying to instead output the probability distribution variable, that is mean and standard deviation vectors. All right, so to sample any new point or to sample any new data from the latent vectors, what we can do is that we can use the means and standard deviation so that we can sample any point in the distributions. To give you a more concrete example, so let's say that if you are having some sort of input data, so we pass this into the encoder map this data into a latent vector. So let's say that our latent vector, our data, when we map it into a latent vector, it constructs a normal distribution like this. Okay. So if we want to sample any data, so for example, when it is mapping, it would probably be something like this. These are the dots that we have in our latent vectors. So if you want to sample any point from these distributions, what we can do, we can specify the mean and standard deviations so that we can pick any point with this mean and standard deviation. We can pick any point under these distributions, okay, under these distributions, so that it gives us a more it gives us a more flexibility so that we can pick any point or we can regenerate. We can choose a new data sample from this distribution. So the model is being able to generate a new set of data. So you guys got the concept. So the overview of VA, instead of just learning any arbitrary functions, the network learn the parameters of probability distributions. All right. So what do I mean by any arbitrary functions? So arbitrary function, which means the encoders, if some sort of function that is mapping from X to Z, right? So this is arbitrary functions. So instead of just learning this mapping function from X to Z, what we are learning is that we are learning this probability distribution parameters, mean and standard deviation instead. Okay. So for example, the intuitions here, if we are giving this image, pass it into the encoders, right? So these are the vector. These are the vector. How many it has? 1, 2, 3, 4, 5, 6. All right. These are the 6-dimensional vectors. 6-dimensional vectors, which is D. C is equal to 6D. All right. And then we pass this. So these are the each elements of the vectors. Right. And then we pass this into a decoder. It can regenerate us a new sample. All right. So it can reconstruct this back with this 6-dimensional vectors value. So using variational autoencoders, by using variational autoencoder, we can describe the latent attributes in probabilistic terms. So instead of this discrete point, right? Instead of discrete point. So this discrete point, for example, it would be minus 0.7 at the zeros, and then probably here at 0.5, something like that. So instead of just a discrete value, we can describe this image as the probability distribution, something like this, to represent this image, to represent this set of image, right? To represent different sort of smile, something like that. So instead of if this smile, instead of just specifying that it is equal to 0.7, so we are seeing that it would be this sort of distributions. If this smile, it would be this sort of distributions. If it is this smile or this smile, it would be something like this. Okay, this represent different degree of smile, right? So then later on, if you want to do some different degree of smile, just a little bit smile, we can pick any point in this under this distribution, so that this phase would be changing. So you will see this in later the lab that we can do that. All right. So instead of just a discrete value, we represent the vector in terms of probability, so that we can regenerate, or we can vary we can vary the degree of flexibility of each characteristic of the data, right? And so for example here, if we have this sort of if we have this sort of smart image, and then we pass it into the encoders, and then this is our latent vectors, right? So we have so if we sample any point from this vector, or from these latent distributions, so what we are expecting is that we are expect that the distributions, so because we are sample from the same distributions, right? So the data is kind of very similar. So we are expecting that these two sample should be very, very similar, because they are sample from the same distributions. Okay. So all in all, the variational autoencoder, it just learn the latent feature Z from data, and then it can sample from the model to generate a new data set. So I think so how can let's first talk about how the models generate a new data, right? So this decoder side. So we can only what we can only see is the X, right, which is our input, and then we want to infer the attributes of Z, so that we want to compute this probability, right? Probability of Z given X, that is our encoder, right? So this is our encoders. So after training, we want to sample a hidden variable Z, which generate a new observation. So this is the decoders. So if you look at this probability equations, right? So this term we can compute using this decoder network. We can compute this by decoder. Why? Because it is what it is that these models is given Z, and then it will generate the probability of X, right? So this model decoder given variable Z, and then it will generate the probability of X. So that's what it implies here. And then P of Z over here, this is what we know, right? So we can assume whatever distribution here we want the model to map it into. But the thing that we don't know is the distributions of P of X, because if you look at the encoder, right, you can have the encoder over here, the encoder, and X over here. So we don't know the distributions of our data set X. So this will be very difficult to compute. So how can we tackle these problems, right? So we cannot use integrals over Z. What we can do is that we can compute, or we can approximate the probability of Z given X by another distributions that is Q of given that is given X, right? Given X over Z over here. So which means that we can approximate this one. Let me just do this. Okay. So what do I mean by approximate this one, right? What do I mean by approximate? So what we are going to do is that, so here our data set, right? We don't know the distribution, whether it would be the normal distributions, or it would be skew to the left or skew to the right. So we don't know the distribution of this. Right? So how can we approximate this one? What we have to do is that we are saying that I don't care about the distributions of the input. But when the encoder learns something here, I wanted to put the data into a normal distribution. So let's say that we are picking the normal distribution over here. All right, because the distribution of X we don't know. And then the distributions of Z, we want it to be normal distributions. So that, which means that we are forcing this encoder to mapping from unknown distribution to normal distributions. All right. So we are trying to approximate this. We are trying to approximate distributions by forcing it to map it to some known distribution that is normal distributions. So that's what we do. Right. So yeah. So for example, this is let me see. All right. So if you look at this latent space of the MNIST dataset, okay, this is the latent space of autoencoders. This is a latent space of variational autoencoder. So if you look at these distributions, you can see that these distributions of variational autoencoder, it looks more like the normal distributions, right? It looks more like normal distribution like that. Okay, so that's why we are forcing the models to project from unknown distribution to a normal distribution. So that's what the autoencoder, variational autoencoder trying to do. All right, so I think I'm just skipping this one. So so as I mentioned, that we can sample or regenerate a new data, a new sample by using variational autoencoders. So after the model learns how to mapping from unknown distributions to normal distributions of our data set. For example, in our data set, we have only this image and this image, right? We have only this image and this image in our data set. After the model learn, the distributions of our data set, what we can do is that we can grab any point from these distributions, and we can regenerate the new sample, that is this one, which never appear in our data set, and this one also never appear in our data set. So we can regenerate this new sample out of that distribution. Okay, so that's why we can generate the something like the face of never exist people, right? So this is another way of, like, for example, we can generate variations of head pose and smile. So many of this image never exist in our dataset. So we can generate that using variational autoencoders. Right. So that's about variational autoencoders. Any questions? So it's more about probability. So yeah. Yeah. So
generated the sample because using the probability instead of using the G factor, pick random sample, random
vector.
Yes, so they can generate it.
So so the only difference is that, so we have the same X, right? We have the same input. If we are using autoencoder, it is going to map to some fixed sample vectors. But if we are using variational autoencoder, instead of just fixing this one, it is going to try to map this into some distributions, some sort of distributions or either normal distribution. So when we want to regenerate, the new set, the new data, so if we are using autoencoder, we have to pick the already mapped vector from here. So we cannot pick any point out of that. But if we are using variational autoencoder, we can pick any point under these distributions, all right? And then we feed it into the decoders. So that's the only difference. So which means that we can generate a new data that never existed before from our data set, right? So that's the variational autoencoders and encoders. So now let's talk about the generative adversarial network. So the question is, what if we just want to sample? Okay, so the idea is there's no explicit model density. So instead of just sample to generate a new instance. So this the problem is that what if we want to sample from a very complex distributions, right? So the distribution that we are most familiar is the Gaussian or normal distribution, right? So we cannot do that directly. So what we have is we have to sample from something simple like noise, right? Like so that we can learn transformations to a data distribution. Right? For example, if we have this what we call a generative networks, or it looks really much like a decoder, right? So in a decoder, we just feed in some sort of vectors, right? And then we want it to generate a new data, all right? Any fake data, we want to generate anything, right? So this is what we want the model to do. We just want to generate something, all right? So in GAN, so how can we do that? How can GAN use to generate the new data, the new data set, the new data sample that never exists before? So GAN consists of two parts, right? It consists of the generators and discriminators, right? So the concept idea is that let's say that you have two people. One is the generator and the other one is the discriminators. Okay, so let's say that the generator is a thief, right, or a cheater, and the discriminator is a cop. Okay, so the generator is trying to generate. So let's say that you have a thief that is trying to generate a fake banks, all right, fake banknotes. And the discriminator is the cop that is trying to distinguish the fake banknote and the real banknote. Okay, so the generator, what the task is that it is have to try to generate as realistic as possible the banknote, so that the discriminators or the cop cannot distinguish between the real and the fake. All right, so that's the only idea about generative. About GAN. So the generator have to, whatever it is, it has to try to generate as realistic as possible, or as real, as close as to the real example, so that this discriminator cannot distinguish. So what we have to do here is that we have some sort of noise, right? We have some sort of noise, any size, any vectors. It just random vectors. We pass this into a generators, right? It looks really much like a decoders, and then trying to generate some fake data over here. And then we pass these fake data into a discriminators, and also we pass it the real data into a discriminator. So the discriminator have to try to identify the real data from the fake one. So which means that if we pass this X real into the discriminators, it needs to identify that this is real. And then if you pass the fake one in, it needs to identify that is fake. All right, so that's the job of the discriminators. So the intuition behind this one is like the discriminator look at both real and fake data, and so it is trying to discriminate between the two. And for the generator, it just starting from trying to imitate the behavior of the real data. So it's trying to create the probability distributions of the real data, right? So let me just, so if you look at this discriminator, right? So it is trying to, the red dot is fake one, the green dot is the real one. So at the very beginnings, the generator can predict distinguish between the real and the fake one. So what the generator learned now, it didn't perform very good, right? Because the discriminator can capture the fake one always by looking at this probability. Okay. So as the training time goes on and goes on, the generator is trying to imitate the distributions of the real data. So as we can see here, now the generator, it's trying to learn the distributions of that. So at some point, the discriminators cannot distinguish between the real and the fake one. Okay, as you can see here, the distributions of the fakes and the real data are very close to each other. So the discriminator cannot distinguish between the two. Okay, so let's look at this one. So the generator just trying to synthesize. Let's say that we have this car. The generator trying to synthesize the fake instance, which is trying to generate any image of the car. So, and then the discriminator trying to identify the synthesized instance from the real data. All right, so that's what it did. And here is the training loss. So it just like a minimax game, right? So if the generators, if the data that is generated by generators or synthesized data is being identified or is being predicted by the discriminator that is fake one, so the generator will get a very high loss and the discriminator will get a very low loss. On the other hand, if the discriminator cannot distinguish the synthesized and the real one, so the discriminators will have a very high loss and the generator will have a very low loss because it can fool the discriminators. All right, so this entire equation just saying that. All right, so we are trying to, so the two generator and discriminator are fighting each other's. One is trying to minimize and one is trying to maximize. So the discriminator is trying to minimize the loss. The generator trying to maximize the comparison between the real and the fake one. Okay. So I think I better skipping this one. So after we keep training that, the generator will get better and better because it's learned, right? So during the learning, we are going to do a back propagation. So what do we mean by that? Because this model, it is nothing but a CNN. It's just a series of CNN. So when we train the models, right, we pass this in, and then we give a prediction, either 0 or 1, and then we do a back propagation. So that we can tell the discriminator that, okay, if you are being able to distinguish between the two, you get low loss. So which means that your parameter is good for now. And then when we do a back propagation as well to the generator here, So if the output from here is being able to identify as a fake one by the discriminators, so the loss value will tell the generator that you are not doing good. You are not doing good yet. So it is trying to update its weight. All right. So we keep repeating this one. So which means that the output from this generator will get better and better. So it will be more realistic to be as close as the real one as the training goes on. Right. So then later on, we can use this after training. We can use these generators to create a new data that never seen before. Right. So that's what the GAN is all about. Right. So after training here, so we can pass like any noise, any vectors that we can sample from any distribution, pass that into this one, and then we can generate this new data that never seen before by the models. Right. It could be any unrealistic data, for example, something like that. Okay. So here is the this is the latent space that the model is learning. So the applications of this GAN, right? So after the first GAN, it's just working with the MNIST data set. So after that, there's many versions of the GAN. So for example, here is the progressive growing GAN. So we can generate a very realistic human faces, right? So these all are fake. So these people never exist in this world. So that is being generated by GAN, right? And also we can doing the conditional GAN, right? So we have some sort of a sketch of the shoes here, and then we give this as a conditions to the generated image. So and then we can generate the image that have a very similar like style with the sketch image that we gave it. So that's the conditional GAN. And also it has been used in many applications for generating a new data set. So here's another example called cycle GAN. So it can swap between zebra and horse. It can swap between different summer and winter, and it can swap from different style of the artist, something like that. So these are the applications of the GAN. So basically, the GAN has been used for synthesize the data set. So for example, in a manufacturers, right? So sometimes it is very difficult for you to capture or to collect the data from the defected pieces of machine or some defected product. You cannot collect all of those. So what they do is that they can use a GAN to synthesize a defected product for them. So that by conditions, doing some conditional GAN, so then we can regenerate a new defected product. So they can use that data to later on training our classifier models. So that's one of the applications of generative model. All right. So in summarize, here's the difference between autoencoders, which consists of encoders and decoders. For autoencoders, it's just mapping from X to some sort of Latin vectors, and then the decoder is trying to reconstruct the input data. Right. For the variational autoencoders, instead of mapping from X to Latin vectors, it is trying to mapping from X to some sort of distributions and predict the parameters of the distribution, that is mean and standard deviations, so that later on we can sample, right? We can sample any point, any data from that distribution, and then feed that vectors into a decoder so we can reconstruct the data. And for the GAN, we have a generators that is trying to generate a new data that is very close or very as real as the real data that we have. And the discriminator is trying to distinguish between the two. All right, so that's the difference between these three generative models. All right, so any questions?
I can use this to create a different code to scam.
What's that? That's scam?
No. We can use a software who detect this video code is real or using AI tool to create.
Mhm. So let me give you some example of when this GAN can be used. So here's the company called Landing AI from Professor Andrew Ng. Yeah, so Landing AI, so they are basically doing computer visions for many types of industry. Right? For example, let me see. Landing Lens. So they have a product called Landing Lens that is mainly doing the computer vision task, right? So when we are collecting the data in manufacturing, right? So you cannot have you cannot collect all the variations of different scenarios. So what you have to do is to synthesize the data, right? Good.
But how much numbers of image should be synthesized? The yes, that's how much. How many of them should be suitable?
It depends. It depends on your applications, and then we cannot say the exact number how many images that we need. It just need to trial and errors to see whether the model is overfitting or not. So that's what we are afraid of. So if you let's say that you probably generate thousands of images, but the model is still overfitting, so which means that we need more data. So so we can't in machine learning models we cannot say examples how many or how many images that we need to make the model good, but it depends on case by case. Like how much or how varies your scenario is. I'm just trying to find you with this the data synthesization case.
Oh, by the way, yesterday I tried Label Studio. I labeled the first image semantic segmentation by myself ever.
Take time, right?
Yeah, it take a long time
Mm.
because it's open source, so need to config this and that.
Mhm. Let me see. I'm not sure they have removed it or not. So
Question.
Yeah.
You work for the inspection machine already before, right? For in manufacturing industry.
Yeah.
So basically it's computer vision task because I work Heineken. I saw a lot of inspection machine. They checking for empty cans or empty bottles. It's
Yeah.
through inspection machine. I check for the level of the fullness of the liquid inside, and they check many checking or even OCR to checking the labels, etc. It's fully computer vision task for learning, or is it OCR? I mean, checking you input the good image and then things like that.
The OCR is also a method. And also, for example, the quality control inspections also that's also computer vision task. And also, for example, here the assembly inspections. So to inspect this kind of PCB board and this electronic manufacturing, they're also using that one as well.
So it's deep learning or is
Uh,
it traditional one?
They are both traditional ones and deep learning models. Some of the tasks that is very easy, some of the tasks that is very easy, we can use just a traditional one. Let me find a video of my work that we did one of that. I'm
Because
not sure.
buying a special machine is very expensive.
Mhm. So so this is the application that we did. This is not learning. It's just a traditional method for inspecting the part from automotive. I think it's motorcycle part. So,
Yeah.
but it's mostly a cylindrical. So here we are using the cameras to check dimensions of this part. So we check whether the inner diameters, outer diameters, the height of the part is good or not. So then if it's good, we reject it into one box. If it doesn't good or defected, we reject it into another box. So this is example of the traditional method. So we didn't do any learning here because we just want to only detect width, height, and the diameters of this cylindrical part. Yeah. Mm-hmm. So these are the computer vision applications that. So basically, in the manufacturer, sometimes you don't need the machine learning models to classify. It depends on the accuracy that you want. So what do I mean by accuracy? For example, in this case, we want the accuracy is high, like 100 microns. So we want that the diameter shouldn't be plus or minus 50 micron, not 150 microns. So by using a traditional computer vision methods, it is better to compute the accuracy in this micron instead of just doing the machine learning. So machine learning would be appropriate for a task like it's good or bad in the sense that it's in presence or something is missing, but not measure the diameters, but not measure the size. Right. So this is measurement, right? This is also a QC inspections. But if you want to detect some missing parts, something like this probably a good example of use case that deep learning can be used. For example, this missing part, and then this sort of defected part, right? So as you can see here, you don't need any dimensional measurement, all right? So you just need to detect whether it's there or not, it's good or bad. It's good or bad in the sense just the look of it, right? Or something like this. If there's scratch or not, it's good or bad. So you don't want to measure the size. But if you go to the use case where you want to measure the size, you want to measure the dimension, something like that, I think the traditional method would work better.
Okay, clear. Thank you.
Yeah, so I'm just trying to find the use case of data synthesizations for this. Let me see. So there are many use cases in this. For example, in this automotive industry, we can also use this to detect a defect, like defected part from the data set. here, for example, here, for example, if you want to inspect a scratch from the car, right? And then in terms of data collections, it would be very labor intensive, right? So to collect the data, to like take pictures of all the scratch apart. So what we can do here is that we can use the same image, all right? We can use the same image, and then let the generative models trying to generate variations of scratch from our data set. So that is another example of how can we synthesize the new data using generative models. So we can just one image, we can probably being able to generate 100 sample out of this one by synthesizing variations of scratch from this image. So going from one image to 100, so it can increase a lot of data sample for training the deep learning models. Yeah. Anyway, I think maybe you can look at this website later. So yeah, there's this an example of how they synthesize the data. Okay, I cannot find the link. Yeah, anyway. All right, so I think we might take a 10 minutes breaks and then come back. I'll walk you through the lab, so it might better give you a better idea of how VAE works, and then we will discuss about GAN also, so that you would have a better idea of how it actually works. All right, so let's come back at 10:44.
your collab link,
Mhm.
do you have to share the directory,
There,
the narrative or the directory?
you mean the orders?
Yes.
Um,
Or it's mouse to your drive.
So you can change that to your drive. Yeah. So what is a good souvenir I should buy from Hanoi? Like snack, and I need to buy some. I want to buy some snack for my colleagues. Any?
Yes. Anything like go to the mark like me because the source is a source of the product and COCP and you can know from where it's from.
Mm-hmm.
Yes, the quality is very good. Nice.
It's mud.
First, in Vietnam, we have special, but this one is very special.
Okay, okay.
Like, I introduce. Okay. For example, for this one is a kind of cake, and this one mean special food panel.
Oh,
Yes.
okay.
For this one is a kind of fruit. I told you yesterday that you only find it in Hanoi, and
Oh, okay.
for another reason in Vietnam they do not have this.
Mhm.
Yes, Saigon do not have this. And
Oh.
Thailand, I cannot translate.
Sweden.
Yes, and this one is the same that I told you. It's not plum, not plum.
Not plum.
Yes,
Okay.
not plum. When you show me the picture of the plum, yes, it's not plum.
Okay, so the same.
Yes, the same.
Okay.
So you can consider for some kind of snack. Yes,
Okay, okay, I see.
yes, and I always go to the mart. Yes.
Winmart.
Winmart belong to Win group.
Okay, okay, I see.
But Fujimat is okay. Fujimat is up on the hand.
I
Yeah.
see, I see. Thank you.
It's near the west leg.
Mhm.
Thầy hỏi mua đặc sản Hà Nội. Để xem là quanh cái lờ Giáp In thầy có thầy ở Nguyễn Trường Tộ giá cái vốn thế mà không biết dịch cho thầy kiểu gì ấy. Cái này không biết dịch cho thầy Yes, very famous. But I cannot translate to English.
It's similar to rice cake or something?
Yes, rice cake, but it's
It's
green rice.
It's not,
Yes, it's not a normal rice.
yeah, I
And,
think.
Ông đi chỉ ra nguyên nhân của hàng than đúng không? Đúng rồi, từ đây thì có thành ra hàng than thì gần bộ luôn. Đó.
Rồi cắt đoạn này, cắt hàng luôn.
Ủa, gần phép nhỉ, 400 mét này. Sao vậy? About 400 meters, and you can go by walk.
Okay.
Yes, near your hotel. Shop here, I think it's over 100 years. We use this for the wedding. Yes, it's a traditional. The wedding we have mud by this. Okay. Wedding.
I see. All right. So I have shared your this link, so maybe you can have a look later. That is, it is like talk about how you make AI work with small data. So here they're describing about how can you overcome the small data problems, right? So one of the example would be using a synthetic data generations. So that is you can collect some sort of a small data set, and then you would use like the GAN, right? You can use GAN variational encoders to generate a new sample of that, so that you can use the generated data to train the models to classify the whether the data, I mean whether the part of the car is good or bad, something like that. All right. So and there are others types of technique, for example, transfer learning, self-supervised learnings, feature learning, something like that. Right? You can have a look at that. Okay, so now let's discuss about the variational autoencoders. Okay, so let's jump right into that. So let's first just connect. So you have to change this part to your own drive. Okay, so let's just run that. Let's run that first. All right, so first thing first, what we have to do is like every machine learning models, what we have to do is we have to set up the hyperparameters. All right, so here we are setting up the learning rate, batch size, and number of epochs. All right, and here we are setting the logging interval. Logging interval means you want to print out, for example, the accuracy, the precisions, something like that. So here we are training for 50 epochs. We probably want to log in every 50 steps. All right. So I hope you remember the difference between epoch, step, iteration, something like that. Okay. So now the data set here, we are going to use the MNIST data set. I think you might be familiar with this data set from machine learning class. Okay. It's just a data set of this digit, right? Black and white digit, handwritten digit, right? So these are the MNIST data set. So in PyTorch, they already prepared that for us. All right, so that's why it's easier for us to try with this. So we don't have to go to collect the data and then prepare the data loaders. So here's how we are going to grab the data that is already provided by PyTorch. All right. So here we import the data set from Torch Visions so that we can use the dataset.mnist, right? And then we specify where we want to download it to. And then we say that we want a training data set, and then we want this data set to perform some transformations. So here's the transformation that we are going to do. So there's nothing much. We are just converting it from image to the tensor. That's it. If you want to try more with, for example, rotation, translations, so you can do so. And here we are downloading for both training and testing dataset. So for testing, you just keep the flag for train is equal to false. And so let's run that. So what we got here is we got 60,000 training images, right? And then after we got the data set, we have to insert it into a data loaders. All right. So oops, the batch site is not defined. Okay, I didn't run this one. Batch site. Okay, we good. So we got the data loader. So now let's see the image size for MNIST dataset would be 28 by 28. All right, and this is our batch site. And then the channels, since it is the black and white, so it has just one channels. Okay, so these are how we're checking the data set. So now defining the models, right? So the first, let's look at this class first. Okay, let's look at this class first. So the VAE, it is nothing but consists of autoencoders. I mean encoder and decoders. So encoder and decoder is nothing but the encoder is just a series of convolution layers, right? As you can see here, the encoders is convolutions. This is one layers, right? Convolutions plus batch norm plus activation functions and plus dropout. So we add dropout just to prevent the overfitting. Okay, and this is one layers. We finish one layer. This is second layers, and this is the third layers, right? And then we flatten out. So we flatten that out. So this is our mean and standard deviation. So how does that work? So for example, here you have a data, right? This is your data set, and the encoder would be a series of convolutions. So we have layer 1, layer 2, layer 3, right? Layer 3, and you have 64 filter and 64 filters. Okay, and then at these layers, so at each layer you have 64 filter, right? And then you at the end here you have flattened it out. Okay, whatever dimension it is here, you have flattened it out to 1 time n. Okay, this is what we call flatten. Okay, because at the end here you have 64 times something x time w h, right? So then you flatten this out. You're gonna get 1 times the result of this. All right. Let's say, for example, we multiply this and then we get 2000. So this flattened vector is going to be 1 by 2000, right? So that's what we call the flattened. All right. After flatten it out, since if you look back into autoencoders, I mean variational, the autoencoder part, right? So we want to spread out the mean, right? The mean and standard deviations. Okay. So we want, after we flatten that out, we want to connect this one to here and one to here. Okay. We want to do that. This why this part is going to do exactly like that. Okay. And after that, we are going to do the decoders. So the decoders, since in latent space, it is very low dimensions, right? So we have to upsample. To match with the original data site. So that's why we need to do a convolutional, a transpose convolutional, right? Like we discussed yesterday. So we're gonna have one layer here. So this one, there's nothing but you convert this, and then you sample some point over here, and then you're gonna get a vectors of this site. Right? You're gonna get a vector of this site, and then you reshape it into a 3 dimensions. Right? You reshape it a three dimensions, because the convolution is taking in a 3-dimensional matrix. Right? You reshape it to match with these layers, so that you can later on perform a transpose convolutions. Right. So that's what we did, 1, 2, 3, 4, and then finally we just we have a trim, right? So after we transport, at the end here, the final it will give us 1 times 29 times 29. So but the original input, it's 28 by 28. So we have to trim it down. So this is how we trim it down. Okay. All right. So this is it. How can we doing the VAE? All right. So here is some sort of parameter trick. So it just how we can pass the perform a back propagation. There's nothing much here. Okay, so here's just a forward part. It's just connecting everything together. Okay, you just you can run that, and then you initialize the models. So this is how your model looks like. Okay, so this is autoencoders. You have mean and standard deviations. You have decoders over here. All right. And if you look at the number of parameters, all right, so this is not a very big models, right? It's just 1,600,000 parameters. Okay. So the loss function is nothing but just mean square errors. Okay. So this one is just how we can compute the loss of autoencoders. All right. So we are using Adams as the optimizer. All right. So the training loop is pretty much the same. All right. The training loop, you start the number of epoch. So you set the models to train mode. Okay. You set the model to train mode. And then for each batch, you do forward part. Okay. You just feed in the model, the data, right? So what you get back, you're going to get decoded data, mean and standard deviation. You can extract that, and also the encoded data. Okay. So in variational autoencoders, there are two parts of the loss function. So the reconstruction loss and KL divergent loss, right? So the reconstruction loss is nothing but the mean square errors, okay? And the KL divergent loss, what is KL divergent? So as I mentioned, that we basically want the encoders to project the distributions of our input from some sort of any distribution to a normal distribution. So this is our preferred distributions, right? So this is our preferred distribution at Z lattice vectors. So any unknown to Z, all right? So when the models keep projecting, first it is probably not normal, but probably it would trying to produce a skew normal. So we add this as a regularization so that the KL divergent is just to measure similarity between the distribution, the two distributions. All right. So that's why we add a KL divergence to force the models to learn the similarity between its generated distribution with the preferred distribution. All right. So we use KL divergence to measure that. Okay. So this is how we compute the KL divergence. So the KL divergence is basically using both the standard deviations and the means that we got from there. Okay, and then here just a pixel-wise loss function. So finally, the loss function will be the combination of these two. Okay, and I think this is it just matters of training. So let's run that. So as you can see, we get the loss going down quite quick from this because it's not that big data set. It's just 60,000 images. So from epoch 1, we got loss of 45, and then let's keep going down. All right, let it just run for a bit. So this part of the code is where we are doing the sample example, the sample vector, right? Because when we do this encoders, we're gonna get means and standard deviations, right? Means and standard deviations. We're going to use these two parameters to sample the data from these distributions, right? So this is where we are doing this sample using these two parameters. So we can sample that. So we're gonna get these Z vectors, so that after that we can pass this into a decoders. All right, so this is where we did it. Right, so the decoder give us some sort of X, and we use that X to get a means and standard deviations. We sample the data, and we pass that data into a decoders. So that's what it does. Okay. So oh, it's, let me see why it took so slow. Yeah, what kind of? I'm not sure I'm connecting to. Oh, okay. Yeah, so we can keep it, make it running first. So in the meantime, there's another interesting data set that I prepared for that. So here's this celebrity vibrational autoencoders. Instead of just creating the image of digit, handwritten digit, so we can use a much better human faces data set, which is called Syllabar. Okay, so everything kind of similar. All right, so you can download this data set from Torch, PyTorch as well, and then the model itself is the same, right? The model is the same. The only thing that is changing is the size of the final layers over here, because the resolutions of the syllabary is 128 by 128. Okay, and the size of the means and standard deviations lattice vector is different. So that's the only thing that we need to change. Okay, and the rest is quite the same. Okay, for example, let's just run. Too many station again. Let me just wait for that. Wait. I think.
Still running.
Yeah, let's just. I'm not sure it's safe. Choice of elapsed time. Anyone finished training? So in the meantime, let's say we can plot the loss. So here, since we are collecting some sort of loss value, right? So here we are logging dictionary. We have a logging dictionary that collecting a loss value and like reconstructed loss, combined loss, and then KL divergent loss. So then we can later on visualize the graph of loss value, right? So this function is nothing but just grabbing those loss values and then plotting it out, and in these functions. And here we are going to generate some sort of the resulted output, and then see what is the latent space looks like. Okay, so let it just generate a bit. Not sure if it gonna works for now. Maybe. I think. Sure how many minutes it's gonna take. It's just halfway. Let me stop it here. Let me just see whether we have anything. Okay, so I just trained for like 20 something epoch. So this is the generated image from our models, right? So here's the latent space that is the models is projecting onto from MNIST dataset and projected onto this latent space. This is it look really much like a normal distributions because we are forcing the models to project the data onto the normal distribution data. And yeah, this is how this is the generated data that we can sample from the data. So this is the result of the models. Okay, so you can have a look at that later. And if we are, let me just change it to, let me disconnect this, and then let's look at the another data set. So if you're setting this directory, so when after the model finish training, it is going to save this. It can give you this like save weight parameters of the models in the directory that you're specifying here. Okay. So let's just grab that, and then this is nothing but just let me reduce this to probably like 15 epochs only. So, so the data set is nothing but we just do a center crop and then converted it to a tensor. And let's see how many data we have in the trainings. Oops, what happened? It says that too many users have viewed it and downloaded this file recently. So maybe it's busy. And let me try again. It didn't allow me to request the data. So probably we're accessing too many users. Too many users have to download this file recently. Okay. Can anyone download this dataset? Celebrity dataset. I cannot do that for now. Okay. Anyway, let's just let's just go to GAN first, and then we might come back for this later. All right, so let's have a look at GAN. All right, let's just connect it to that. Right. So let me try. So we are going to try with the MNIST again for the Gantt, okay? And then let me see. So and then what we are going to do next is we are going to specify this latent dimensions, right? This latent dimension is this Z, the noise, right? Where we are going to sample the data from to feed in as the input to the generators, right? So here we are changing to 100 dimensions, okay? And these are the hyperparameters. Since we have discriminators and generators, so we have to specify the learning rate of the two models, right? And then the batch size and the number of epochs, okay? And this image size is nothing but the size of the MNIST dataset. So these are the hyperparameters that we need to check. And this is the MNIST, just trying to load in the MNIST. And let's see the MNIST, okay. So this is our data set. So the generators, right, as I mentioned, the generator is nothing but looks like the decoders from autoencoder, right? So which means that we have to upsample, right? We have to upsample the input to match the dimensions of the real image, or to match the dimensions of the input of discriminators, which is 28 by 28. Right. So what we are doing here is that first we are just using here. Let's see. So the latent dimension is this one, this red rectangle here. That is 100, right, in our case. And image dimension is 1 by 28 by 1 by 28. And then we are going to define a blocks, okay? A blocks of that would be, so here instead of doing a convolutions, we are just using a fully connected layers, right? So so what we are doing here is that instead of convolutions, we are doing fully connected layer. Right, we are doing fully connected layer. Right, because our input is just a vectors of 100 dimension, right? So we don't have to do our convolutions. We just feed this in 100 dimensional vectors into a fully connected layers, or we call linear layers here. All right, and then make it like many layers, and then at the end here, we just so at the end we probably end up with some sort of batch size by x. So then later we are going to turn x into 28 by 28, right? So this is 2D. We are turning that into 3D, which is a batch size matched with 28 by 28 at the end of this. Right. So this is where we are converting from a vectors to a matrix. Okay, that is batch by with 28 by 128 by 28. So this is it. And for the discriminators, it's just nothing but it's just like the simple classifiers. Right? It's just layers of linear layers of fully connected layer connected together. Okay. It's just a simple classifier over here. Okay. This is generators, and this is discriminators. So we initialize the two. All right. So this is our models. This is how it looks like. So to things to note here. At the final layers, right? We are using a tan edge, right? So why do we use tan edge here? Why do we use tan edge? Why not sigmoid? Why not others?
It's minus to 1, right? I think.
Okay.
What's that? Minus 1 to 1.
It's the range.
So yeah, why do we want minus 1 to 1?
Okay, let me think. Why we need minus 1? So you want to classify? No, it's not. It's the decoder. I mean, this generator, right?
It's the generators.
So why we need that one? Generate. You generate the image, and then the output of the generator is negative. What does it mean?
So it is 1 to 1, right? So the tan edge is 1 to 1, isn't it?
Minus
Minus
1 to 1. You think?
So what is the value of this pixel?
0 and 255.
Mm-hmm. Isn't it 0 to 255?
I mean, yeah, it's binary, right?
Mm-hmm.
It's binary. So white is 0, right? White is there. White 255. And gray is 5.
So first you have to look at this value of the image, right? First you have to look at the value of this image. What is the what we need the models, the generator to do is to predict the pixel value, right? The generator needs to predict a pixel value.
Mm-hmm.
So what you have to do is you have to know what is the value of each pixel here. So we want to predict each and individual pixel value from that's what we want the generator to do, right? So that so the reason why we use tan edge. What? Any guess?
So you
Can-
predict and you minus, which means that you predict wrong. No.
Mm.
No,
Yeah.
such thing. You predict pixel by pixel, and you turn the value minus.
So can you check the values and the pixel values of this data set? Can you write a code to check what is the values of a pixel, just one image? What is the range of that one? Is it minus 1 to 1, the range of this pixel in this image? So we have to know that the image, each and every image, we are performing the normalization as well, right? So we were performing normalizations 0.5 and 0.5 over there. So we need to take that into account as well. So basically the pixel value will fall under minus 1 and 1. So that's why we use a tan edge over here. So and then the last layers of the discriminators, we are using a sigmoid function, because the discriminator is just going to predict whether the image is real or fake, 0 or 1. 0. So that's why we use sigmoid. Okay. So and then here we are just pushing So let's see this is the numbers of parameters for the generators, and this is the number of parameters of discriminators. So for the loss function, we're using nothing but just Bernoulli cross entropy, because the loss functions that we are going to measure is whether the models is predicting the discriminator can predict correctly or not, right? So that's that's our loss functions. Okay. So the optimizer we are using Adam for both of the image. I think this training is pretty much the same. So we have a real image. We retrieve a real image and the real labels, and then this one we just sample any value, right? So what we are preparing here is this part. We are preparing this part, X real and Y real, right? This is what we were preparing. And this one, Z, that we randomly sample. So this is what we randomly sample, right? To match the number of batch size and the Latin dimensions. Right? And then we feed this Z into the generators, and the generator generate a fake image. All right, and then we give a fake image a label, which is 0 over here. All right, and then this is the part that we are using the generator to generate a fake image. And then after that, we are going to train the discriminators. We're going to train the discriminator with the reals and the fake image. Okay, so we are giving the discriminator the real image first, and then let it predict. And then we are giving it a fake image, let it predict, and then calculate the loss for both, and combine the loss for the discriminators. All right, and then we perform a back propagation. And now for the generators, here we are feeding in the fake image into the discriminators. All right, so the loss functions of the discriminators depends on whether the loss functions or the loss values of generators depends on the performance of discriminators, right? If discriminators perform good, which means it's correctly classified fake as fake, real as real, so the loss value of the generator will goes up. Otherwise, it will goes down. So that's why we calculate the loss of the generators depends on the performance of discriminators over here. Right. So the rest is nothing but just to log in and save the model, something like that. Okay. So that's two part. Okay. So you're training the discriminators over here, calculating the loss. When training the discriminators, you have to input both real and fake image. All right. And when you are training the generator, which means you're measuring the performance of the generators, you just feed in the fake image into the discriminators to measure that performance of the realistic of the generated image. Okay, let's just run that. Oops, how much? Ooh, 100 epochs. Okay, so I think we wouldn't. So yeah, it's going down. So let me just stop that. I think I already have this weight. So let me just show you other things. So I have already trained this model once. So I already have this weight of the model saved once in my folder here. This is generators, discriminators. This is what I have. Okay, so here, I think here just to print out this is the loss of discriminators and the generator. Okay, so what it's supposed to do is that the loss of the discriminators they also should go down to some extent. It will go down anyway. Oops. Okay, so so here's the risk. I think I need to train to some extent so that we can grab some example to show you. So what I want to show you is that the result, the improvement from the result that generated image from the generators, how it is being improved over time. Okay. Let me just run that login. Let me just train for maybe 20 or something, 20 epochs, so that we can have a look at what the generated image look like. So if you look at the epoch zeros, so this is what it looks like, the resulted from generators, and then we will later see like epoch 1, epoch 2, epoch 3 up to epoch 5, how the result is improved over time. Okay. Let's just wait for a moment. So in the meantime, you guys have any questions regarding the code or maybe about the lecture? So let it run for maybe 10 epochs. I think it's pretty slow. I ran the other day. It's much faster.
You use T4?
Yeah.
Let me run for 800.
Yeah, probably 800 is faster, I think.
Yeah.
Okay, I think 10 is enough. So let's see the loss values. So this is how the loss value, right? So the discriminators looking okay. The generator losses keep going down. I think if you keep training, it goes down and converge anyway. So let's look at the visualizations of the improvements from epoch 0, and then this is epoch 5. So it looks much better than the epoch 0, right? So if you look at this one, so if you keep training, and training, so I think it will look much better, and then it will look very much like the original data set. And one thing that you probably have to, if you want it to convert faster, you probably might need to increase the number of parameters. I mean, you can increase the number of layers in the generators and the discriminators, so then it will learn faster, and then it can learn a more complex representation. So we can add more layers and then increase the number of neuron per layers over here. So probably, for example, we can add this more linear layers over here, and then we can increase this number of neurons over here, so that the generators can learn much faster with more number of parameters, as well as the discriminators. We can increase the number of layer as well. Okay, so I think that's another way you can do to increase the performance of GAN. Okay. Yeah, so that is GAN. Any questions? Let me go back to this one, whether we can run it or not. Let me go back to VAE. Okay, it didn't allow me to download again. So can you guys download this? I mean, can you run this still in your OLAP?
We check.
Drop
We check.
EC lab. Not sure whether it's really happened to me or anything.
VAE Silibar, right? The notebook.
It says that too many users have viewed and downloaded this file recently. So I think if you run just 9 people, I don't think that's too many. That's not too many. So yeah, maybe it's happened only to me, or I'm not sure.
Same. I got the same.
You got the same?
Yeah.
Okay, I see.
Which data set is it?
It's
Silibar.
Silibar. Yeah. So maybe the other sides of the world, they are also learning VAES. So maybe other university, or they are also teaching VAE at the same time. So, so this is the one that we are using. Silibar.
Celeb A, right? Okay, celebrity.
So basically, this is what it's gonna look like. It is a large scale celeb basis attributes. So here's, for example, celebrity with different facial expressions, with glasses, with wavy hair, something like that. So we are going to train this VAE. So then after that, we can doing the vector subtractions or additions, so that we can see a variations of what we can play with the models. So let me give you a concrete idea of what we see. So I think So if we finish training the models like CRF VAE, so we probably can grab some of the property from the faces, making like adding something, subtracting something for them, and then it will create another faces with different facial expressions, something like that. So that's what we can do with that.
So it's
So,
same like work to back plus
yeah.
minus the works, and then you have the king, the queen, something like that.
Yeah, right. So the code at the end here, this is what we can do we can do a subtraction, something like that, from the Latin vectors. So you can extract you can sample some of the Latin vectors, and then you add or subtract some of the elements from that vectors. So then you can see different different types of faces with glass or not, something like that. Okay, so maybe you can try this yourself, because for now we cannot download the data set, so that I cannot demonstrate this part. Yeah, so maybe you can try that later for yourself. Let me try it again. So why not? Okay, no luck. Okay, so this is it. Any questions about Gantt and VAE?
Just
Right.
play around. Thank you.
So maybe you can play around with the code to get more intuitive about what we have learned about what is the generators, how can we sample the noise, what is the latent vectors, how can we sample the latent vectors from some sort of latent space, how can we in terms of VAE, how can we like sample these latent features using the parameters of the distributions, right? So that's what we have learned, right? So I think if you walk through, if you've gone through the tutorials or the lab, it will give you a much more sense of what we have been discussing. All right, so then maybe this is it for this morning. So I'll see you guys in the afternoon at 1. So in the afternoon, we will discuss about the 3D visions, 3D deep learning. So I'll introduce you a little bit to another world. So what we have been discussing so far is just about 2D. All right, so next we are going to discuss about the 3D. All right, so I'll see you at 1.
Okay. Have a nice lunch.
Okay.
Go bún chả. Try bún chả before.
Bún chả, yeah, I tried it.
So what else you can eat? Phở gà, chicken phở.
Yeah, sure.
Anh cũng ăn phở tối qua thôi.
Thế à? Ê, ăn gì? Bún đậu, bấm tôm à?
Have you ever tried shrimp pate?
Shrimp pate?
Yes, in Vietnam.
No, not yet.
Không, bún đậu mắm tôm cơ mà. They eat noodle with tofu, fried tofu and pork meat and shrimp pate. I think it's very difficult to eat with somebody never tried before.
Bún móc đi. Bún móc bữa ăn rồi. Ở Sài Gòn vẫn ăn bún móc rồi.
Có điểm NLP chưa qua?
Em đâu biết đâu. Không hỏi. Busy quá rồi. nhắn tin mấy anh bên trường hỏi thử.
Anh tưởng em chơi thân Duyên, hỏi xem Duyên có chấm không chưa?
Em chả thân với ai. Thôi em đi ăn cơm đây, em đói bụng quá rồi. Okay, have good lunch.
Okay. See you guys at 1.
Đi kiếm ăn bún chả thôi. You try bún chả before?
Yeah. We can have her, no problem.
Okay, we have rice with chicken, we have dog meat. First restaurant dog meat is opposite the restaurant yesterday.
Yeah.
Yes, famous. Recent in Vietnam called Việt Chi.
Mm.
Yes.
Yeah, but I don't eat dog.
But if I do not tell you this is a dog meat, how do you know?
No, I don't know.
You don't know.
Thử giả cày coi.
All right, so you can grab the slides from the chat box because I cannot upload it to Teal because the file is too big for Teal. So yeah, I'm just sharing with you in the chat box, so you can grab the slide from there. It's in PDF format. Okay. Right. So let's get started. So here's the introductions to 3D deep learnings or 3D visions, right? So 3D deep learning is some sort of a subset of 3D visions, right? So since we have been discussing about the learning methods in computer vision. So now we are going to talk about, instead of from 2D, now we are going to talk about 3D. What is 3D deep learning? Okay. So 3D deep learning, it's kind of subset of a bigger umbrella that is called geometric deep learning, right? So geometric deep learning is considered of geometric processing. So the applications of geometric deep learning would be, for example, for drug discovery. So why drug discovery is related to geometric deep learning is because in drug discovery, we have some sort of, for example, the protein structure. So the protein structure is in 3D. So that's why geometric deep learning also works with the applications of drug discovery or any medical any medical application, for example, medical MRI scanning, which is also in 3D. And also self-driving car networks also can be works with geometric deep learning. For example, the application that we are most familiar with is the map, right? So when you want to go from one place to another place, it's kind of network within the Google Map. So as you can see, the Google Map has been very accurate for the time estimations. So it's because of the geometric deep learning that they apply these kind of techniques into Google Map network so that it can better predict the estimated time for any trips. Right? And also, of course, robotics had to work with 3D, real world 3D. So it is one of the application of geometric deep learning as well as AR and VR. All right. And in terms of geometric deep learning, there's a term called 5Gs, which consists of the grid, graph, group, geodesics, and gauge, something like that. So these 5Gs are just types of input or types of data that we can represent into geometric deep learning. Right. So when we are speaking about this 3D deep learning, first let's look at what is the geometric processing task, right? So geometric processing is all about reconstruction, remeasuring, shape assist, or like filtering, something like that. If any one of you were the mechanical engineering, so you have been used geometric processing along the way. Like for example, when you want to model something, you want to model a mouse, you want to model a machinery part, something like that. So those are those are involved geometric processing tasks, right? For example, SolidWorks, AutoCAD, something like that. So those are the applications of geometric processing task. Right, here's the example of geometric processing, for example, compressions. So every object that we represent in the computer on our screen, so we probably call this a polygon mesh, right? So a polygon mesh is nothing but consists of a node and the edge connected together to construct a surface, right? So this is what we call a polygon mesh. So it consists of a triangles, so we call a triangulations, right? So at every point of this one, we have a node, and then each node connected together with the edges to construct one surfaces. All right, so that's why we call a mesh or a polygon mesh. So a polygon mesh, which means that we are not limited to just a triangle. So it could be a hexagon or any polygon. And if you look at the geometric pipeline, if you look at the geometric processing pipeline, it will start from the input. How can we capture or how can we acquire the 3D structure or 3D informations, right, from the input? For example, we have a CAD models, we have a scanning, right? We have a scanning sensor, 3D scanning sensor. So after we acquire or after we capture the 3D structures of an object, so later on we can first remove some noise from the one that we captures, and then after that we can use those information, use those 3D input for further analysis. For example, in car manufacturing, they can use a scanner, 3D scanner, to scan the surface of the car and then analyze the surface quality of the car. And then we can further, from there, we can further do, for example, smoothing the noise to make the surface more smoother, something like that. So these are more about improve the quality of the reconstructed surfaces or reconstructed data that we receive from the 3D scanners. So the geometric deep learning is the field of deep learning that aim to generalize the neural network models to non-Euclidean. So the non-Euclidean domain would be such as a graph or a manifold. Okay? So the polygon mesh can be viewed as a graph because it consists of a node, which is a vertices, and edges connect the node together. So it constructs some sort of graph. So like I mentioned, the application of geometric deep learning, for example, here's the process of drug discovery. So in order for humans or in order for researchers to come up with a new type of drugs, they have to go through like lots of experiments. So that take them a lot of time to come up with some sort of drugs or medicine, right? Because it has to go through a different experiment, different mixture of chemical structure. So the geometric deep learning here comes in to help it can shorten the time to come up with a new drugs formulations, right? Because we can predict what kind of, so if we mix two types of atoms of a chemical structure, if we mix them together, what kind of structure, what kind of protein structure that it will come up, and then we can simulate the effect of this protein structure with the new chemical, so that it speed up the process of a drug discovery. And for another application would be the traffic maps, right? So if you look at the ETA in Google Maps, it has been improved very much in the past 5 or 10 years. The accuracy is very, very good for now, I think. So if you look at the map here, we can view this as a graph as well, because point from one location to another location can be viewed as the node, and then the road connecting from one point to another point can be viewed as edges, so that this can be constructed as a graph, so that after a graph, we can apply the geometric deep learning models to help us to predict the ETA time. Okay. And another application would be a recommendation system. For example, if you are using Facebook, right? So sometimes Facebook will suggest you some friends who probably have a similar property like you or like any of your friends. So for example, you might have a friends who know another friends that, so Facebook see your connections, but not direct connections. So they might recommend that friend whether you know him or her or not. All right. So this kind of recommendation system also one of the applications of geometric deep learning. Or even when you watch a movie in Netflix, so the recommendation movies also kind of similar to this application, because under the hood, Netflix also have a recommendation system to recommend you the movie that is similar to what you have watched. And also, here's another application of geometric deep learning, that is a self-driving car. So I think 90% or 99% of the self-driving car that has been developed in the world, they are equipped with what we call a LiDAR sensor, right? So a LiDAR sensor this blue dot and green dot here, this is what a LiDAR sensor see. All right. So the LiDAR sensor, it's just a sensor that is spit out the ray of signals and then calculate the time that signal go and come back to the sensor. So then we can measure the distance between the car and the objects ahead. So this is what we call a point cloud, right? So this is a point cloud of that. So that's what the self-driving car see. So what we have to do next is that we have to take this point cloud and then try to detect what is another car, which part of the point cloud that the car see is another car or another person's or a road or pedestrian. So these are another applications of geometric deep learning that is helping the car to see through the world or a 3D world, right? So, and another application would be AR/VR. So I think like 5-10 years ago, the Oculus from I don't remember, it's Microsoft or something. They have this sort of AR/VR devices that we can map a 3D structure. So helping doctors to visualize through anatomies of the patients, so that they can analyze the patients before they make some surgery or something like that. Or even though they help medical students to study the anatomy instead of just going direct into a real bodies. So they are using this to help the medical students to study the anatomy of humans' bodies. Or another application would be a robotics. So in manufacturers, you can use the robot arms that is equipped with a 3D sensor, like a 3D scanner, to scan the part of the car or any part from any products, so that you can measure whether the one that already machined match with the one that we decide. All right. So for example, we decide this mouse, and then after, so we decide this mouse in computers, right, in a CAD models. All right. So, and then after it's being produced, so we want to measure whether the size of the real mouse and the mouse that we design in computers, they are matched or not. So we can use the 3D scanner to scan to get the informations about the point cloud of this one, and then we can use that to map them together with the CAD models, so that we can compute the difference between the models, the one that we design in computers and the one that has been produced. All right, so this is another applications of geometric deep learning. So here's some sort of 5G, that is the input to that can be categorized, the input that we can use with geometric deep learning, that is grid, group, graph, and geodesic. Right? So we are not going into all of this. We are going into just some of them. So now let us talk about a 3D deep learning. Right? So we will discuss about 3D representations, 3D data set, and then we will go into different category of 3D deep learning, from image-based, voxel-based, point-based, implicit functions, and mesh-based. So I'll walk you through each and every one of this to see what are they, and then how can we use them. So let's talk about the 3D representation. So in this lecture, we are going to focus only on the grids and the graph on the 5Ds. So here's the 3D representations. So these are the way that we can representation 3D information from the real world. So we can categorize the 3D representation into a subgroup, that is Euclidean structure and non-Euclidean structure. for the Euclidean structure, for example, we can achieve the RGBD information from the depth cameras, right? The depth camera in which it can capture the RGB, just normal image, along with the depth informations of the image. So that's what we call the RGBD. And another one is the volumetrics, right? A volumetrics can be a voxel. So a voxel is nothing but a small cube, right? A small cube that is connected together in a 3D space. It's just a cube, a box, right? A small box. It's like a Rubik cube, right? So then you can put them together to represent any shape, all right? So that's what we call voxel. Voxel is nothing but a box, a rectangle box, okay? And the octree is just another way to represent different size of the box, so that we can put it, we can like structure them into a different shape that we want. And another one would be a multi-view. So to reconstruct a 3D structures of any objects, we can take the image from many views, the same objects from many views. So then after that, we can use the traditional computer visions, like we have to calibrate the camera first, and then after that we can use the calibrated information to stitch the image together and then construct the 3D information from there. All right. So these are the example of the Euclidean structured data. So for the non-Euclidean data, so the first one would be a point cloud, right? So the point cloud is nothing but just a point in 3D space, right? So each and every point, it represents the surface of an object. Right? Point cloud tell us only the surface of an object. Right? It can represent XYZ coordinates within the space. And another one would be a graph and the polygon mesh, right? The mesh and the graph is very they are interconnected, right? So the polygon mesh is nothing but you connect a dot together to complete one triangle. So one triangle represents a graph. So one triangle represents a surface of an image. Right. So these are the 3D representation that we are going to look at and then see how they can be used with the deep learning models, right? From image-based volumetrics, point cloud, and the side distance function, is the implicit surface functions, and the polygon mesh. So like I mentioned in our very early lecture, that deep learning models, either 3D or 2D, they are driving with the data set, right? Without data set, we cannot do anything with the deep learning models, right? So we need a deep learning model is very data hungry, so it needs a lot of data to train and to learn from. Right? So the deep learning kind of started after 2D because the difficulty for us to collect the 3D data, that is kind of difficult. So starting from like 2015 onward, so there are many 3D data set has been available, so that the development of 3D deep learning has been started from there. So the data set, the example of the data set that we can use to train models would be, for example, a model net and a shape net from Princeton University. So they have collected the CAD model from many places, and then just put them together into the models. Or the ABC dataset from Scotech and MIT. So these are the example of data set with different applications. For example, the ScanNet is also the simulations or the data that they get from a scanning device and collect the data as the data set. And for the self-driving car, there are two to three open data set. So one called Kitty data set. All right. So these are from the university, ETH University. So they have a project that driving a car that is equipped with a LiDAR sensor around the cities, and then trying to collect the data, trying to collect the point cloud, and then use a human to label part of the point cloud, whether where's the car, where's the road, where's the pedestrian, something like that. And another data set is from Waymo, which is the company under Google or Alphabet. So they also have a fleet of a car that also equipped with a LiDAR sensor as well. And it has been driving around San Francisco and collect those data and trying to label the data so that we can later use to train the 3D models. So these are the example of the data set that has been used and has helped the 3D deep learning community to jumpstart for training the models. All right. So here's another example of data set which used to predict a human gesture, also trying to map from 2D to 3D example. So the library that we can use to work with 3D deep learning, so PyTorch, they have developed the PyTorch 3D so that we can represent the polygon mesh data, the point cloud data, in such a way that we can feed it into a 3D deep learning models, like a convolutional neural network, something like that. So PyTorch just develop this library to help us like faster and to help us doing this sort of 3D deep learning much easier. And there are also another libraries like PyTorch on geometry or JAX, DryMesh, Deep Graph libraries, and Open3D. So these are the library that we can use to manipulate or use to process the 3D information, either point cloud, polygon mesh, or any kind of graph, something like that. Okay. And from TensorFlow, so TensorFlow also have TensorFlow graphics that also work with the 3D information as well. Right. So now let's look at the first 3D representations. How can we use this representation with the 3D models? So the purpose of this is that we want to develop, right? We want to develop a deep learning models that try to predict a class. All right, it is a image. It is a 3D predictions. All right. For example, if you have the image of an object, if taking the image of an object from different views, so this is what we call multi-view CNN, right, for 3D shape recognition. So we want to know whether this is a chair, this is a car, this is a chair, this is a car, this is a table or not. So we can capture in this work, in this paper, they just try to do what they try to do is that capture the image of an object from different view and then pass it to a CNN, and then it's just a normal CNN, right? Because what they are doing here is that they are just taking the image. All right, it's just like you are passing through the image into a CNN network, and then try to combine the information from all the view together, and then pass it into another CNN, so that the model can predict whether what class or what kind of object it is. All right, it's either the bed, the chair, the desk, or the toilet, something like that. All right, and so that's the image base. So basically, the image base is the advantage is very simple. We can reuse the standard component of the CNN, right? And then it is very efficient. However, the memories of the system that we want to use it's not that good, and there's no geometric information involved in image base because it's just the image, all right? It has no other information, for example, the depth or the size of the objects, and it has no invariance to, for example, translation, rotation, something like that. So that's the image-based 3D deep learning model. So we have taking the image from different view, pass it into the networks, and then the network just predict the class of the objects of interest. So the next one would be volumetrics. So the volumetrics. So the purpose of this one is still the same, right? So we want to classify, or we want to predict the class of an object. For example, in this paper, 3D ShapeNet, so what they are doing is that they are converting a depth map of the input, and then converting this into a volumetric representations, or we call a voxel, right? And then they are just doing a 3D convolutions, right? So the 3D convolution is, let me give you what do we mean by 3D convolution? So 2D convolution is, for example, this is your image, right? This is your image. So your image is 2D, right? Width and height, and then you perform a filtering with, let's say, 3x3, right? You convolve this with this. This is 2D convolution. So what do we mean by 3D? So this one, volumetrics, right? It is just a voxel. A voxel is just like a cube. You have a cube like this. You have a cube like this, right? And then you have a small cube inside, right? It's like a grid, but it's in 3D grid, right? It's like a 3D grid. If you can imagine, like a Rubik cube. So this 3D grid. So when we are talking about 3D convolution, which means that this is 3D, right? You have height and width and depth, right? So when you are doing 3D convolutions, instead of just 2D kernels, right? You have 3D kernels, or you have 3D filters. You have 3D filters here, for example, 3x3. You have 3x3, and then you convolve this just like the 2D one, but you convolve with 3D. All right, cube convolve with cube. So this is what we call a 3D convolution. Okay, it's just pretty much the same, but adding additional information. All right. So by using this one, we can feed in a voxel representations into the 3D CNN, so that finally the models can learn the representations of the volumetrics representation of any shape of any objects. So then we can predict the class of the objects, right? So the question is, why do we need to predict a class of a 3D? Why not just use 2D? All right. So in like self-driving car, you sometimes you don't have a 2D information. You only have 3D. All right. So that's why we need to have this sort of models to be able to work and then identify whether the object it see in front is whether a car, a pedestrian, a bike, or a bicycle, something like that. Okay. And also in 2D, we can use scan. We can use scan to generate a 2D image from some sort of noise, right? So in 3D, we can also generate a 3D structure. We can generate a 3D informations from some sort of noise as well by using a 3D convolutional 3D convolutional layers. All right. So if you look at these papers, they're going from this sort of oops. They are going from this 1 and Z over here, and then performing a 3D convolution, upsampling, and then they can generate a new objects, a 3D new objects. A voxel base, right? Like I mentioned, a voxel can also turn into the octree, right? The octree is another representation. It's just like a subset of voxel again, but it just represent the data in different ways. So what do we mean by octrees, right? So if we look at a voxel in terms of 2D, okay, if we have this sheet of papers, if we split them into 3 parts like this, so this is what we call voxel, right? This is what we call voxel. But if we keep splitting, let's say that, for example, my object is somewhere around here, right? So I see that this 2 is empty, right? So I don't want to further split them. So then I further split this two grid or 2 voxel. So I split it into another 4 equal space over here. So we keep doing this. We keep dividing this, right? We keep dividing this. 4 until we get unto 8, right? Because of is mean 8, right? We keep dividing that until 8 layers. All right. If you look at this one, you look at this, the cube divided into 4, right? 4 in this dimension, 4 in this dimensions, and then keep dividing each dimensions until we reach the 8 layers. So that's what we call octree. All right. So the third one that I just want to introduce to you is the side distance functions, right? So what is the side distance function? So this is what we call the implicit representations. All right. So the side distance function, for example, I have this object, right? And then I want to know whether, so I have these objects, and then I want to know which part of this voxel is inside or outside the object area. So what I'm doing is that, for example, here I have a circle object, and then I put a grid over this circle. I want to know which box here is inside and which box is outside. I want to know the surface. I want to know the surface of an object. Okay. So then what we are going to do is that we are going to calculate the distance between this point to the surface of an object here. So if the distance is positive, which means it's inside. If the distance is negative, which means it's outside. If the distance is 0, which means it's exactly on the surface of an object. All right, so that's what we call a side distance functions. So from here, we can see that the orange point is the point that inside the objects, and the blue point is the point that outside the objects, and the gray point over here is the point that is inside on the surface of an object. All right, so by using this one, we know the boundaries of an object, right? We know the boundary of an object. So so here, so if we have a side distance function, so this is the polygon mesh, right? This is the polygon mesh, and then we turn this polygon mesh into a side distance function. All right, so this dark blue here means this inside, and then the other color is mean the outside of this object. So what we are doing to turn this polygon mesh into a side distance function, we just push a box, a grid of box in around this object. All right, and then we are calculating For example, we are saying that we want to split this into, let's say 5 by 5, 5 by 5 by 5 grid, for example, in each direction. So we want to know which box that is inside and then which box is outside the surface of this one. So finally, we end up with these types of side distance function in 3D. All right. So the question is, how can we go back from these side distance functions to the mesh again? Because we are going from the mesh to side distance functions. And then the question is, how can we go back from side distance function to the mesh? So we can use the algorithm called the Marching cube. Okay. So the Marching cube, so since inside this box, it's just a cube, right? It just contains of small cube inside this box. It's contain a very small cube inside this box. So for each box, we already know that whether it's inside or outside the box. So we can use these conditions to check whether that box is fully inside or fully outside, or part of them is inside, part of them is outside, something like that. So then we can reconstruct this surface back. And so we can use this Marching cube to train the models so that we can predict the class of the objects. So by using these implicit representations, it can be very efficient, simple, and very accurate. But the downside is that it cannot handle the invariance, for example, the rotations and translation invariance of the data. So that is the third 3D representation. So the fourth one would be the point cloud. Okay. So let me introduce you what is the point cloud. Right? So the point cloud is a set of points which can be represented by its coordinate x, y, z in a 3D space. Right? Right. So the point cloud. So the point cloud is just a point, right? It's just a point in 3D space. It can be. Sure. Right? So so the point cloud is just a set of point, right? It's just a set of point. So for example, what do we mean by set of point? And it can be represented by x, y, z coordinate. For example, this point. Let's say that this is our 3D space, right? 3D space, and then this point can be, for example, x, y, and z. So we have some point around here. We have some point around. So let's say that it at x of 10, y of 20, and z of let's say 5, something like that. So this point, it just at location 10, 20, and then 5. All right. So this is the value of this point. This is the value of this point. It's coordinate. So if many points put together, so that's what we call a cloud of points, or the point cloud. So there are two types of point cloud. There are two types of point cloud. One is called unorganized point cloud. So unorganized and the organized point cloud. The difference is it just in the matters of how they store in the RAM or in the memory. Right. So the unorganized point cloud is that the point that are close to each other in a 3D space, they are not stored close to each other in the memory. But if it is organized point cloud, which means if the point that are close together in a 3D space, they are putting them together next to each other. For example, this green and blue point over here, they're close to each others in a 3D space. So we are putting them, this is our memory, okay, this is our memory. So we are putting them in the memory close together. So this is what we call the organized point cloud. So by doing this, we know the relationship between the point. So we know that point green and blue, they're close to each other in this organized point cloud. Okay, but most of the point cloud that we got from the sensor, like a LiDAR, like 3D scanner, they are unorganized point, right? They are unorganized point cloud. Most of them, I would say 90% are unorganized point cloud. All right, so the benefit of point cloud is that the point cloud, it can be converted into different representations. It can be converted to a polygon mesh. It can be converted to a depth image. It can be converted to a voxel representations. So this make a point cloud is very flexible and scalable representations. And it is very simple because it's just only a point, no connectivity. All right. So we don't have to store any connectivity, just a point X, Y, Z. That's it. And then the point cloud is very close to a raw sensor data, and it is very easy to acquire by using a 3D sensors. So that's why many applications they start from point cloud. And then after that, if you want a polygon mesh, you can convert this point cloud to polygon mesh. Or if you want a depth image, you can convert the point cloud to depth image. So that's make the point cloud very simple and flexible to use. So how the point cloud is being generated, how it is being generated. So there are four ways, right? So the first sensor is what we call a passive stereo, right? So what do we mean by a passive stereo? So the passive is the sensor that is consists of two cameras. Okay? It consists of two cameras that is pointing out. So we know the distance between the two cameras, right? We know the distance between the two cameras, and then we capture the cameras capture the image. So they will see a similar thing. So then what you have to do to calculate the distance from the objects and the cameras is to use the triangle, right? So the triangle theory, right? So here we know the distance between these cameras. So we know this D, and then these cameras taking this image. This camera taking this image of an object, right? So what we are going to do next, we are going to use the epipolar plane to calculate the correspondence between the two, right? So after that, we can use this triangulation method to find the distance between these cameras and this object by using that. So we capture the image just using a traditional computer vision or image processing. You calibrate this camera together, you know the distance between them. You take the image from the two cameras, right? So there must be the overlapping between this image and this image. So you calculate the correspondence of the features that appear in these two images, so that after that you can use a triangulation to calculate the distance between the image and between the cameras and the object. So this is what we call a passive, because there's no moving information. It's just the cameras, right? So the second way that we can capture the point cloud is to use active stereo. So the active stereo consists of two cameras, right? Two cameras, and we have a projectors. Okay, we have a very small projectors. So the projector project a pattern, right? Project some sort of pattern. These are the pattern that the projector project onto the objects, and then we capture the image Okay, we use these two cameras to capture the image, and then we can compute the deviations. We can compute the deviation of these patterns. How is that? For example, you have an object curving like that, okay, and you project. You have an object curving like that. You project this pattern, right? So the pattern would be the pattern that projects on this surface. Let's say this pattern. It won't be this flat, right? It will be, for example, something like this. It will go along the curve, right? When you project the patterns onto that one. So we can calculate the difference between these predefined patterns and the pattern that we captures from this image. We can calculate the difference between the two. So then we can infer the distance from these deviations of the patterns. All right, so the example of this sort of active stereo is the Intel RealSense. So Intel RealSense here, it has two cameras and then one projector over here. So we can use it to capture to capture the point cloud or to capture the depth image as well. All right. And the third way is we call a structured light. Right? It works very similar with the active stereo, but just with one projectors and one cameras. That's it. Okay. So we know the distance between the projectors and the cameras, and then the projector just project the pattern again. This camera just compute the deviation of the patterns with the projectors. All right. So it worked kind of similar, but have only one cameras. And the last one would be a time of flight. All right. Time of flight. The camera, this sort of camera is kind of, for example, a LiDAR or a 3D scanners, right? So the way it works is that it has a light source, for example, the infrared light source. So the infrared light source, it's just a ray of light that is going through hit the surface of an object and then come back. All right. So we know the speed of light. We know the speed of light. So we just calculate the time it travels from the camera from the sensor to the surface and come back. So, for example, I have a ray of light travel from me to the wall. So it go back and forth, taking like 2 seconds, right? So let's say that the speed of light is 1 second, right? It's 1 second. So that which means that this wall would be probably let's say 50 meters, something like that. So if we know the speed of light, and then we know the time it takes, so we can calculate the distance. So if you go back to physics class, all right, is V is equal to S divided by T, right? So if you know the speed, you know the velocity, you can calculate the time. And then S is distance, not. So V is equal to S divided by T, right? So if you know the speed of light, if you know the time it takes, you can calculate the distance between the objects and the light source. So that is the how we can use a time of flight to get the point cloud. All right. So this Velodyne time of flight or LiDAR, we call it LiDAR. That most of the self-driving car they're using to do that. And also in our iPhone, we have, I think it have a LiDAR sensor in here. All right. So because when you're using the facial scanners, it has the LiDAR turning on. Okay. And also the 3D scanner like this, they have a LiDAR sensor as well, or time of flight sensor. So what we get is the point cloud from there. All right. So after we acquire the point cloud, so we can do many things from the data that we can acquire. For example, if we want to scan these entire rooms, we want to create a 3D structures of these entire rooms instead of just using a measure tape to measures and then draw this room in SolidWorks or in other software like Blender, something like that. So we can use a 3D scanner to scan the entire rooms and then stitch the image together, filter out, finding some sort of key point, finding features, and then reconstruct the surface or even perform a segmentations, whether in this room consists of the wall, consists of the tables, consists of the chairs, something like that. All right. So we can use the point cloud processing to perform the analysis on the point cloud. So we can do both using a traditional algorithm that is like trying to filter out the noise, trying to perform the key point extraction, something like that, or we can now use with a learning-based model as well. So what is the point cloud registration? So for example, if you have a very big automotive parts, and then we want to scan them, right? So when you scan this kind of, we have a 3D scanner, you only scan a part of the entire objects. Right? When you scan once you get another part, you scan another time, you get another part, and then you combine them together. Okay, so when you combine them together, this is what we call a point cloud registration. All right, so which means that you combine the point cloud from different angle, from different viewpoint together. All right, so that's what we call a point cloud registration. So after we perform the point cloud registration to get the entire model, 3D model, 3D structures, so we can perform any other task. For example, like we can perform the object classifications, we can perform the reconstructions, right? From the point cloud, we want to perform the reconstruction to get a polygon mesh so that it has a surface information, so that we can further do a pre-processing so that we can achieve the 3D structure back again, or even though we can do the segmentation as well. So the first paper that I want to introduce you, and this paper we are going to have a hands-on with the lab, is the PointNet. All right, the PointNet is the first paper that they are using a point cloud with a deep learning models. All right, so what is the task that the PointNet does is the classification. That is, it classifies whether the objects or the point cloud is belong to the tables, it belong to the cars, it belong to a mark, something like that. And it is also perform the part segmentation, right? For example, the planes, the wing, the bodies, and the tail of the plane. And also it can perform semantic segmentations. For example, the rooms consist of the wall, the table, the chair. So that's the task that PointNet can do. So the architectures of the PointNet is very simple. Okay? It's very simple. Since it's just a series of fully connected layers. All right, it's nothing much. It's just a series of fully connected layers and convolutional layers. Right. So the PointNet itself, right? Like I mentioned, when we have a point cloud, most of the point cloud are unordered or we call orderless, right? So for example, this point cloud consists of these many dimensions. So basically, this D, it would be X, Y, Z, right? Which is 3D, 3 dimensions. And N here is the number of points. Let's say that we have like a 1,000 point, right? 1,000 point, right? So this is the first point, this is the second point, this is the third point, this is the fourth point, right? So what do we mean by orderless point? Which means that if we shuffle the orders of this point, if we shuffle the order of this point, shuffle from here to here, So the entire point here and the entire point here, they represent the same objects, right? They represent the same object regardless of the orders of the point. So that's what we call the orderless point cloud or unordered point cloud. All right. Let me just skip this one. Right. So the point at it just what we have to do is we just pass in this n by 3, which is n point, and 3 is the coordinates of the point cloud, right? So we pass this in the another networks. So it is the just like a convolutional neural networks, and then so in 3D, what we have to consider is the orientations and translations, right? For example, this kind of chair, and this kind of chair, and this kind of chair, right? So they have different orientations, right? So when we pass the point cloud of these two into the network should be able to classify them as a chair. It doesn't matter the orientations of this chair, and also it shouldn't be matters of the translations or orientations of the point cloud. So the model should be able to classify them as a chair. Okay, so that's why we have this sort of input transformation to learn about the transformations, rotations, translations of the objects, and then later on we just want the other part of the models to capture the features of the point cloud. Okay. All right. So this is just the structures of classification network. So finally, we just pass it into a multi-layer perceptrons, and then take a max pooling, and then after that we just do another multi-layer perceptron, and then ask the model to predict what class of an object of the point cloud that we feed it. So for the segmentations, we can do the same, but instead of just predicting one number, we predicting the n by m. So the n by m here, n is the number of point, and n here is the number of class, number of segment that we want the models to predict. For example, in our data set, we have 5 segments. 5 segments mean, for example, a wall, a table, a chair, something like that. So we want to classify whether each individual point belong to which objects in the scene. Okay, so that's what we call segmentations. All right, so here's the example of the output from PointNet, right? It can perform a segmentation, for example, a tabletop, a legs, right? And the plane would be a body, a wings, and a tails of the plane, something like that. All right, so using point cloud to train the 3D deep learning model, it better than other types of input data like from multi-view or voxel. It saves much more memory, 80%, right? It used less memory than the other types of the data. Okay, and so the limitations of that is that it cannot learn like multiple level of abstractions. There's some limitations. Right. So I think this one I might not go into much detail. It will confuse you guys more. So because it's kind of the deeper in terms of that. Right. So it just like using different techniques to process the point cloud to return them for different sort of tasks. For example, classifications or segmentation tasks. So last, I will introduce the mesh-based that So this is what we call a polygon mesh. Okay, this is what we call a polygon mesh. It consists of vertices and edges. Right. So a polygon mesh it has vertices, edges, and faces. Right. Face is the triangulations. It is a triangle that consists of 3 points and three edges to construct one faces. All right. So one surface can have many triangles. So there's a paper called Mesh CNN. So they are feeding the polygon mesh into the network so that the network learn to extract the patterns from the polygon mesh, so that the models is being able to classify the objects, whether what kind of object this polygon mesh belong to. Right. So they just use different techniques to learn about how the models is going to learn on edges, how they are going to learn the relationship between edges, how they are going to learn about when the models rotate and translate, how it is being changed of the edge and the vertices. So they also come up with some sort of kind of the mesh poolings, so to finally help the models converge faster, to reduce the size of the data. Okay, so anyway, finally, what it does is just a classification task and the segmentation task, whether the part of the object is belong to what objects, and then what kind of part of the object it is. So yeah, so the mesh will also do the segmentation. They are just try to segment different part of an object, the body, the legs, the hands, the foot, something like that. Okay, because it can learn the relationship between the part of an object. All right, so I think so this one they also like give you the example of what this TART is doing, is that they are just passing in the 3D models of a human face, a human head, and then also pass in the voice of a person, of any person. So then what they are trying to do is that they are trying to simulate, all right? They are trying to simulate how the people speak. So to map the voice, and then to make the mouse move, right? To make the mouse move according to the word that they are saying. So before training these models, what they have to do first is to determine the point on the mouth that is correspond to any word that you are saying. For example, when you are saying hi, right? When you're saying hi, so this is your mouth. This is the mouth. So they have to determine the point over here. So because this is the polygon mesh, right? This is the polygon mesh. It consists of a point and a vertices that connect together. All right. So this is your mouth. And when you are saying some words, right? When you're saying some words, these points are moving, right? So first they have to define, when you are saying some words, how is this point move from the original shape. So then what they are trying to do is that trying to map each and every word from this voice, from this audio to this point, how it is going to move according to the audio that provided. All right. So so finally, this is what it looks like. Can I play it? No. No. I didn't play.
Picture.
It's the play button. Anyway, it didn't work. I don't know. Anyway, so the mouth will move according to the voice. Okay. So to summarize, So here's the 3D representation that we can use to train the 3D deep learning models. So each of them have a pro and cons, right? For example, the image based, they're very simple, good result, but it doesn't provide any geometric informations to the models. But the point cloud, for example, it is very efficient, simple, and it's accurate, but it cannot deal with the invariance, like for example, rotation or translation that good. All right. So it depends on the applications, what kind of representation we can choose to use for the 3D representation. All right. So there are many more topics in 3D vision. This is just a surface of what we have seen in 3D vision, right? So in other topics in 3D vision, for example, multi-view studio, structure for motions, 3D sensor, and all those related to computer graphics. So those are the 3D vision area as well. So let me just real quick show you this. Let me show you this. I just want to show this result. Capture learning and synthesize of 3D speaking style. Capture, what is it? Capture learning and synthesis of the speaking style. Okay. So
learning model trained across many subjects. First, the input audio is transformed onto a low-dimensional embedding using deep speech.
okay, so I think I just maybe speed.
Legal society was based on hierarchies. My desires are simple. Give me one informative paragraph on the subject.
All right.
My desires are simple. Give me a folder will help to prevent warping. A cardboard.
So as you can see, so as you can see here, so this is a polygon mesh. Okay, this is a polygon mesh. This is not a triangle. So if a triangle mesh, you will see this one. It consists of three points. This is a polygon mesh. So it's it's a square. It's not square. It's a rectangle, not a rectangle. It's just 4 of this one. So this is what we call a polygon mesh. So in order for this mouse to move, you just have to move the point, right? You have to move the point and change the length of each edges around this mount. Okay. So what they are doing is that trying to map the audio to this point position, to the positions of the point around the mount. So that's what the model learned, trying to map the audio with the mount movement. Okay. So that's what it does. If you can see that the point and the length of the edges keep changing around the mount. So that's how they do it, right? So the data set that they have is this kind of 3D models of this head. They have a 3D model of that, and then trying to make human speaking. And here's another example. I think you might see many times. So they are trying to map a 3D. So this is 2D, right? This is the video, and then they are trying to map this 3D. So this one is 3D structures onto the face. So this is a shade mesh, and this is a mesh normals. So that's what they are trying to do. So you have a 3D structures, and then mapping between the 2D and 3D, right? Mapping between the 2D and 3D. So yeah, so as you can see, there's a point on the face. So you have to first performing the the face recognitions detect a key point and then map those key points to the 3D models. And another applications, I think this one, maybe this is a deepfake. Let me see. So we can use Obama face, and then we can make him speak anything. All right.
NBC glad.
Yeah. So we can make him to speak any way, any voice we want him to do. So we just starting from 3Ds and then mapping his mouth movement style, right? And his mouth movement style to map to this image or to these videos, so that we can manipulate him. Okay. And any other? Yep. Probably. Yeah. This is some sort of the applications of 3D deep learning that I just want to introduce you. So any questions? All right. If no questions, maybe let's take 10 minutes break. Come back at 2:30. So then I'm going to walk you through this PointNet to give you a more sense of what is point cloud, how can we feed it into a neural network so that it can learn to perform a classification. All right. So let's come back at 2:30. All right, let's get started with our last lab of the course. All right, this is the last lab of this course. So this is PointNet, okay? So let's first, in this 3D, so let's first just, let me show. There's T4 GPU, probably enough, okay? So let's first just bring, we're going to use PyTorch again, and then also, what is that? Let me just install some sort of library, that is path. Okay, just run that one. So so now here we are going to download the dataset called ModelNet. All right, so let me see ModelNet 10. So this dataset is collected by a group of researchers from Princeton University, right? So they have a varieties of ModelNet. So they have ModelNet 10, ModelNet 40s. So the ModelNet 10, it consists of 10 classes of the objects, right? So in this ModelNet 10, it has 127,000 CAD models. So then we are going to use this small data set to train the PointNet to see how it works. All right. So let's just first download the models net. It roughly about, I'm not sure, 400 megabyte or something. And then after that, we are going to unzip it and then put it. So it is going to download into this sessions storage. Okay. So yeah, it's roughly about 250 megabyte, right? So after, so this is, you can see this is the download image, I mean zip file. And then let's just wait for it to unzip. So in this unzip, there are 10 photos, right? 10 photos for each object, from bath to bed, chair, desk, dresser, monitor, nightstand, sofa, table, and toilets. All right, so these are the 10 objects or 10 classes that we are going to work with. Right? And so yeah, here's the class ranging from 0 to 9, right? So the polygon mesh or triangulations, it consists of, it can be represented in the different types of formats, for example, .off, .obj, something like that. So it just matters of how they organize the data, all right, how they organize the vertices, how they organize the faces. So the most common one would be .off and .obj. And there also another that would be .ply, right? So let's read in some example, right, of .off. So here we are going to read in this from bed, right? So in this OFF, there are 2095 vertices. All right, there are 2095 vertices. So let's look at what it looks like. So this is polygon mesh. Okay, so this is polygon mesh that we collected from this. So you can see this is a surface, right? This is a surface. So now let's look at what is the poly. This is a point, right? This is a vertices. This is a vertices. So going from here, which is consists of vertices and faces. So here we just remove the surface, and then we want to see whether what kind of vertices that these objects consist of. These are the vertices of the bed, of that bed. Okay, and then the connection between these vertices will brings up these 3D models, that is polygon mesh. Okay, this is pretty much it. That's it. Okay, so this is what we call a point cloud, right? So this is just a point cloud that we grab. So the point cloud is nothing but the point X, Y, Z, right? This is the vertices of that. All right. If you point at any point in this one, you can see that this point is at the locations of X minus 26.1143, Y is at the location of 32, and Z at location of 7, right? So each and every point, it has the coordinates of X, Y, Z, right? So then we can take this as a point cloud, but this point cloud, it just very like similar to the vertices of the models. It doesn't tell us any surface information, right? It doesn't give us any surface information about that one. So let's sample some point cloud that it will give us a surface representation. All right. So here is the point cloud that we sample, right? That we sample from the surface of the bed. So what do I mean by sample? What do I mean by sample? So if you look at this one, right? So we have a surface over here. When we sample means that we just pick any point. We just pick any point from the surface. We just pick any point, randomly pick any point from the surface, right? So that's why we got this point cloud. This is the point cloud that we randomly sample from the surface of an object. So as you can see here, we can now, it looks more like the bed above, right? It looks more like the bed above. So this is how we call the point cloud representations of that, right? So here we sample 3,000 points. Let's make it like 10,000. Let's see how it's going to work. So this is 10,000 points. We just randomly pick 10,000 points. All right. So the denser or the more number of points you sample from the surface, the more information you can have about that surface. If you can compare this is look very much like the original polygon mesh that we have earlier, right? So this is what we call a point cloud, right? So we have each and every point has its own X and Y, X, Y, Z coordinates. Okay. So this is point cloud. So now, if you look at this coordinate, right? If you look at this coordinate of the point cloud, you can see that they are ranging from minus to plus something, right? So for different models of different objects, they might have different size, right? They might have different size. So the range of this data would be very varies. All right. So before we can put this data into a machine learning models, we will do basically pretty much the same as the image, right? So we have to normalize them so that the value of X, Y, Z will be in the same range for every object. Right. So this is how we normalize. So we are going to normalize it into a unit sphere. Okay. So this is how we are going to normalize it. So after normalizing, you can see that this value is ranging from I think it's -1 to 1. I believe Yeah. So it's ranging from -1 to 1. So this is what we call a unit sphere, right? A unit sphere is nothing but a sphere that sit. This is the unit sphere. Let me just find you the image of this unit sphere. Right, so this is how a unit sphere look like. This is the sphere, and it has a radius of 1. So that's what we call a unit sphere. Okay, so we are just, so it's ranging from -1 to 1. So we are just normalized every objects or every models to fit within this sphere, so it has a similar range. Okay, so this is what we got after we normalize things. Okay. So like in image or in 2D classifications, we can augment the objects, like for example, randomly rotate, randomly translate them. But in here, we are just want to randomly rotate and add some noise to the input point cloud, right? So what do we mean by adding some noise? As you can see, if you look at each and every point in here, we are adding some kind of noise, which means that we are adding some numbers into coordinate x, y, z of that point. So it shifts a little bit from its original positions. So if you compare this point cloud with this point cloud, right, with this point cloud, as you can see, this point cloud looks much better without noise, right? So, but in the real world, when we are using the 3D scanner to capture, there is always a noise in there. So we want the models to handle a noise as well. So that's why we are introducing the noise into this the data, right? So as you can see here, we have a noise. This point is jumping out from the original positions, right? So so next, we are going to just convert that into a tensor. Okay. So we do data augmentations, convert it into a tensor. Okay. And then so in PointNet, we are going to use 1024 points as an input. All right. We are going to use 1024 points. So that's why we are going to sample 1024 points for each and every objects to get that point cloud, and then we are going to normalize them, which is this, putting it into a sphere, right? Putting into a unit sphere. That is, we are normalizing them, and then we can augment the data by random rotations and randomly add noise to the point cloud, right? So now we can create a data set, right? So the data set we have is that we have to give it a class. So we know a class of every objects, right? Because in these photos, each and every object in this photo are categorized as the class of an objects. Okay, so we can do pretty much the same with the image by using this get item, right? So we have a point cloud. We have a point cloud of that along with its labels. So this is its label, right? Category. This is the label of that point cloud. Okay. So for each point cloud here, we read in the data, we transform it, right? We transform it, and then we just put them in folders into the folder. After we sample the point cloud, we put it into the folders along with the categories labels. Okay. And if we want to do any transformations like normalizations, add noise, or randomly rotate the objects, we can do so in this data set. All right. So here is our transform functions that we are going to do. We sample for each and every objects or .off here. So we're gonna have .off. This is the .off. Right. For each .off, we are going to first sample 1074 points, and then from those points, we are going to normalize it into a unit sphere, randomly rotate in the z directions, randomly add noise, and then convert them to the tensors. So it just pretty much the same as how we did it in 2D, right? And then we just prepare our training and validating data set over here. Okay. So this is just listing out the class. There's nothing much. So we have a totals of 3,991 training sample and 900 validation sample of total 10 classes. Okay, and the size of each point cloud will be 1024 by 3. 3 represent not RGB but XYZ. Okay, and now it's time to prepare the data loaders, right? So we prepare the transformations, we prepare the data set, and then we put that data set into a data loader, right? It's pretty much the same what we did with 2D. Now let's look at the model architectures of the PointNets, right? So if you look at PointNets, let me grab. So if you look at these architectures of the PointNets, we're gonna see that it consists of this input transform, which is just a layers of multi-layer perceptron, and followed by the multi-layer perceptron, followed by another feature transform that is a series of multi-layer perceptron, right? And then at the end, we just take a max pooling of that and ask it to predict the categories. So what we do here is that using a 1D convolution. So what we have been discussing so far for 2D, right? For 2D, we are using 2D convolutions. 2D convolution means that your filter here, this is your input, okay? Your filter here is either 3 by 3, 3 by 3, 7 by 7, 5 by 5. So this is what we are denoted as COF 2D, right? COF 2D. But what is COF 1D? All right, COF 1D is the convolution with the filters of one rectangle, one element. All right, so that's it. All right, instead of 3 by 3, 4 by 4, you have 1 by 1. Right, so that's the COF 1D. Right. So you have a series of this COF 1D. This is COF 1D, right? The number of filters, size of the filters, in and out, in and out, in and out. You just connect them, followed by a linear layers. For each layers, we have a batch norm, right? So this is the TNet, this TNet, right? This TNet over here, this TNet over here, and the forward is nothing. You just connect them together, right? And another transform here is also a series of convolutions followed by the batch norm for each and every layers, right? And for the main layers here, multi-layer perceptron over here, it's just a series of linear layers, right? Just here of linear layers over there. Let's just run that. So the loss functions, we can do like a classification loss, but this one it's just a little bit complex. So yeah, they're using this LNN loss. So all in all, it's just a simple classification loss. There is nothing much. Right. So the the rest will be pretty much the same what we do, setting up the optimizer learning rate, right? And then the training loop is pretty much the same, right? As you can see here, you extract the data, you feed in the data into the models, perform a back propagations, and then calculate some losses, and then validate the models. Okay, let's just run that. Let's just run the training. Is it trained? Let me see. It takes quite some time to load in the data into the GPU. Now it's getting slow. I'm not sure it's trying to train or not. I think what it is going to do now, it's just going through preparing the sample data and then trying to sample the point cloud, pre-process the data, something like. So what it is doing now, it is just trying to prepare data loaders, right? Trying to process that. So this is the transformation that it does. So that's why it takes quite some time, because there are like roughly 4,000 objects it needs to sample the data and then normalize it, adding noise, make a rotations of that. So I think that's why it takes quite some time. But when it start training, like when it finishing the preparation, like now it finish preparations, and then it start to train the models. I think it will take quite some time. Yeah, it take kind of long. 2 minutes in, we just haven't finished one epoch. So we just finished 20 sample. So I think I'll wait it just for one epoch so that it can save the model, so then we can try to test it. We can to see whether we can test it or not. How many epoch? So set it to 15 epochs, and then I think one epoch will take like 10 minutes or something like that, because it's just 30 batch. As you can see, the loss just goes down, giving code goes down and down. So after that, it will perform the validations, right? Perform validation. So here we switching the models from dot trained over here to dot eval, so that it won't calculate any it won't it won't consider a dropout. It just remove the dropout and change the behavior. And when we are doing the torch.nograd, so it won't calculate any gradients, and then it won't perform any back propagation, so that we can validate the models from here. Okay. So maybe let's wait a little bit. So I just wanted to save the models here at this one, because the code here is that we want to save the models. We want to save the models for every epoch, right? So here we are going to we just like finish 1/3 of the entire data set. It haven't saved the model yet. So in the meantime, any questions about point cloud? How we sample it, or how can we manipulate it? How can we adding some noise, something like that?
But so driving car, they still use this kind of point cloud as to the what they call a sensor or radar image to.
Yeah.
But I saw that they still, I mean, a couple of video they still use the segmentation on the street. Is it a way to, I mean, combination?
It is use a combination of sensor. So for example, this is Waymo, right? So this Waymo, it has a taxi service in San Francisco, California. So as you can see here, self-driving car is not only rely on LiDAR. It rely on many sensor, like sonar sensor for the range, and also rely on the LiDAR sensor. It's also rely on the cameras as well. All right. So what they're going to do in self-driving car, they are doing what is called a sensor fusion. All right. The sensor fusion is that you combine the informations from many sensors together and then to perform some task. For example, the segmentations can be done by using the image. All right. And the image can use for segmentation, but for detecting a very long range objects and then planning the part of the car ahead, they might rely on the LiDARs, because the LiDAR can see very far, and then it can plan a long time ahead, and then it can also detect an object, a more precise object. So then they probably combine the segmentations from 2D, that is from the cameras, combine it with a data that is being segmented by using a LiDAR sensor together. So it's just a combination of sensors to perform the same task.
Okay. Maybe it can happen in America only.
Yeah, probably, because it also depends on the law as well. So yeah, because in the US, there's only some certain state that allow this car to be drive on the road. For example, these are the list that they have. For example, from LA, Phoenix, San Francisco, Atlanta, and Austin, Texas. So these are the only 6 places that the state has been allowed them to operate the self-driving car. And also for Waymo, they also way more data set. They also open their data set so that others can use for learning or something. So if you're like want to play around, so they are opens their data so that you can use this data to let me see. Yeah, you can use this data, for example, for they have a challenge. If you have a free time and you want to participate in the challenge, so they have like a segmentations, object detections. Yeah, there are many things. So these are the challenge that they have, and the data set they have already have a label data set so that you can use this data set to create some applications or to train deep learning models. So you can have a look at this data set and then try to play around with it. Okay. Right. For example, the 3D semantic segmentation, 3D camera only detections, right? Because they have a camera only detection as well, but they have a real-time 3D tracking, 2D detection, 2D tracking, or real-time 3D track detection as well. Yeah, so there are many data sets you can do, and then they have a challenge. Yeah. And what about end-to-end? Yeah. So here like this is the view from the cameras from the front and the back of the car. Right. So what is in so they have many sort of behaviors, right? This is cut in something like that. So when we decided when we like training the models, we have to handle this kind of situation. Different like stores, different behavior, driving behavior, something like that. So it has a deer like jumping around, something like that.
Cross
And also they have some road blocks, something like that. Yeah. So this can be fun if you have some time and you want to play around with the data set of self-driving car. And you want to play with point cloud or not point cloud. These are the data set that you can have your hands on. All right. Let's see, not one batch, oh, almost. See, I think the accuracy is getting better and better. From 1.9 to now down to 0.9. Maybe another minute it would finish the first epoch. So if like when I did my PhD and then I tried these models, and then we have some sort of GPU in the lab, it wouldn't take like much time. It take like not 10 minutes to finish the like 10-20 epochs. I think T4 GPU is kind of slow, but it's free anyway. We can't complain.
I currently use 800. It's still slow.
800 still slow?
Yeah, my time is, I mean, still at the same speed as you, but the loss a little bit lower.
Okay. Even 800 still slow. Interesting.
Yeah, I still haven't finished my first effort yet.
Let's see. Yeah, just give it 2 more minutes, I think, and we'll finish that, and then we can have the safe models. So then we can test it, how good it is for one epoch. So this paper is kind of very first paper that trying to use the point cloud, trying to use a point cloud as an input. Right? So then after that, there are many papers that coming out applying the 3D deep learning. I mean the deep learning models with 3D data. Not yet.
Yes, finished the first.
You finished the first epoch?
Yeah, accuracy 54%.
Okay.
Oh, you got 59.
Yeah, I got it. That is saved. Where did it save my?
The new version.
It saved the models. I think it is trying to save the models now. If save is true, it should be trying to save the models. So let's wait a little bit. I'll stop it for now. Then let's see, we can retrieve it or not. See.
Some student feels sleepy. We change topic to final exam. Wake up.
Yeah, I don't know, but why didn't it save for this part? Save, saves. No, not here. Anyways, maybe you can try later. Yeah. It seems that it doesn't run this line of code. Oh, this should be changed to true. Yeah, this should be changed to true so that it can save, but I didn't. Anyway, you can try to change this to true, and then it will save your models for every epoch, so then we can test it. Okay, anyway. Yeah, so that is it for the POINT-X. Right? Any questions? Okay, now let me discuss about, let me wrap up the class a little bit. All right, so we have been together for almost a month. All right, so we have been studying from the very low level vision, from image processing, features detection, feature descriptions, right? So those are the traditional methods for detecting the objects, for classifying the objects, or to perform some image processing using a very traditional computer vision methods. And then we also have been discussing about the learning-based methods for computer visions, right? Starting from the image classification using a very simple like KNN linear classifiers. And then after that, we also discuss about deep learning models for the objects, object classifications, object detection methods, all right? And also we also learning yesterday, learning about the image segmentation using both traditionals and learning-based methods. And today we wrapped up the course with generative models, that is autoencoder, variational autoencoders, and the GAN. And then in this afternoon, we are learning about the basic of 3D visions and 3D deep learning. How can we represent the 3D data, and how can we use the point cloud as an example of 3D informations or 3D representation to feed it into the deep learning models. All right. So this pretty much about the data-driven computer vision course. I hope it's give you some ideas or some sense of what it look like for the data-driven computer visions. So I try to combine both traditionals and learning method. So to cover the scenario where sometimes you might not be able to use a learning method, but you can use a traditional method to handle or to address the problems. Right. So so we're going. So there are two things left, right? So as I mentioned in the very first class, so this class we are going to have. Let me remind you of this. Let me go back. Let me remind you of the grading policy. So the grading policy. So there will be a 30% of mini projects, right? So whoever haven't submit your slides or your code, please do so. So that's 30% of the point. And then the final projects, all right, the final project is another 30%, right? And the final exam will be 40%, okay? So in the final project, I think I already give you the instruction for that, okay? So you can find the instructions for the projects in the announcement here. So in the final projects announcements, I already described what it is, right? So so the final project will offer you a chance to apply all the concepts that we have learned in this course into it could be to your final project could be in either one of these categories, that is, for example, applications. So if you have any specific backgrounds of your interest, so you can apply the computer vision concept into your applications. All right, you can choose a real world issues and use vision to address it. Or in another way, you can develop a new models. If you have some sort of idea, you can develop a new models or modify the existing one to tackle any computer vision task, right? So it shouldn't be you are taking the existing one and doing the same task, but you should take the existing models and doing some other tasks that this model has never been done before. Okay, so one limitation, just keep in mind that this course is computer vision course. So we are mostly dealing with the image or the 3D data, but not NLP, right? So we are not going to do that. But so in your final project, it should be more about computer vision, more about image, videos, or the 3D information, not more into natural language processing. Okay. So here's the structures of the report. So the report should be between 4 to 6 pages. And I also provide you the link. You provided a link for the template. You have to follow that template. Okay. So the report should be structured as this. Okay, should be structured as this. more or less. So the type, the abstract, the introductions, the related works, the data. So the data is like what kind of data you are using, how you get it, and then how you pre-process it, how you treat the data. And then another section would be methodologies. What is your approach? What are the problems that you are trying to tackle? Something like that. And then the experiment, discussing about how do you experiment with the models, how you solve the problems, what are the experiments that you are experimenting with, and then the conclusions and also the reference. Right. These are the structures that are very similar to the paper, to most of the paper that has been published. So the deadline will be July midnight, July 27 midnight. All right, so that is the deadline. That is I believe it's Sunday. Yeah, it's Sunday 27 midnight. Okay. Which is 1 week after the final. Okay. And the final will be on June 20th from 9 to 12. Right. And the final, so the final will include everything. Yeah. So the final, the questions can come from any lecture we have. All right. So the formats of the final would be, for example, I will give you a Colab notebook like this. A Colab notebook like this. Let me give you a sense of what it's going to look like. All right, so I will give you a notebook like this with a questions. Okay, so with a questions, give me a moment. So for example, I will give you a notebook with question one like this. It should be something like that. So there are two types of questions. Okay, there are two types of questions. The first one would be ask you to describe or ask you to explain something. Explain or describe. So you have to explain the concept or that is related to the questions. For example, I would ask you to explain the concept of linear shift invariant system, for example. Right. So you have to write your answers in terms of the markdown format. For example, this is my answer. So you just write it in this notebook, right? Explaining things. And then another types of question would be ask you for coding. Okay. Question 2, for example. Question I will ask you to implement or modify the code, something like that. So you just coding along the way here. You just put your code, run your code, and then show the result. All right. So after you finish, you just share this. You just share your notebook. You just share and then give the access to me. All right. So that's it. That's how it is going to be. And the exam is open book, open web. All right. And when you are working with this sort of Colab, so we cannot prevent you from using generative models. So you can talk with ChatGPT, but you cannot talk to each other. You cannot talk to other students. You can talk to ChatGPT, you can talk to Gemini, but please do not copy the answers from ChatGPT or Gemini, but answer in your own words. Okay. So in the exam day, we will ask you to come to the office. So for those who are in Ho Chi Minh, you have to go to Ho Chi Minh office. For those who are in Hanoi, you have to come here in Hanoi office. And then we will ask you sitting in this room. So we have a camera right there. And then I will join in from Thailand. And then we will split you in the breakout room for each individual one, right? And then we are going to monitor. So I'll have a student from AIT coming in as a TA to look at the monitors, so that we know that you are not copying from ChatGPT directly. Your answer from your understanding. All right. So, and then we also, the reason we ask you to come to the office is because we don't want you to talk to anyone. That's it. Okay. So to summarize, you can use generative AI. You can search the web. You can open the book. All right. But when you answer, you have to answer in your own words. And when you code, all right, when you code, you should provide a comment as well. So then we know that, yeah, I know that the generative AI can also give you the comment as well. But wherever possible, just insert the comments in the code so that I can read through all your code and then understand what you are trying to say. Okay. So any questions about the final?
Very clear.
Okay. So please be reminded that the grading will be depend on this three part: mini project, final projects, and final exam.
Oh, I just finished the experiment
Mhm.
for the final project.
Okay. All right. So for the mini projects, there's one person missing, not submit your documents. Is it you?
No, it's not. It's me. It's me. Khoa, the T-Rex one.
So maybe you can, if you have his contact, just tell him to submit the document.
Yes.
Is he the guy that he present his mini project in Pagoda? Is it?
Yes, that's the guy.
Okay, yeah. So just maybe you can tell him to submit this one, because that's cost 30% of the final grading. All right. So any other questions?
Very clear.
Right. So so I'll end this course, and I hope you guys getting something out of the course, and probably maybe in the futures, if you want to work with computer visions, this course probably give you some basic idea of understanding, and then apply it to maybe futures job, for example. Okay. All right.
Yeah.
I think maybe this is it for the course. Thank you everyone for joining the course, and then I will see you next Sunday. So be prepared. That's 40% of the grade.
I will be there.
Okay. Okay, sure. Please make sure everyone can come to the office. All right. then this is it. Bye-bye. Thank you.
Bye. Thank you.
Thank you.
Bye bye, thank you.
Bye bye, sir. Thank you.
I use this my